right, let's go then from I think I'm already there. Can you see my PowerPoint here is small at the bottom, right? Okay. Let me go on and start from the current slide, and it should take up the whole screen then. Okay. There we go. All right. Now, you can't see it, but I can, and it messes me up, is this taskbar is right in the middle of the slides. So I'm going to scoot that down here at the bottom. Okay. And is this where you remembered? No, this isn't it. Let me scroll down a few slides. This says leave off from where we did before, but this is where we were before, right? Waves and cyclones. Okay. Now, Valerie, you sounded very low level there. Okay, wait. Here comes one. Let me get him in here. So the top part of the alphabet is trying to make a comeback here. Okay. Yeah, you're fine. I was just afraid my headset was going out. But okay, got it. Yeah, you moved away from the mic, huh? Okay. Okay, good. Good to know it's not mine falling apart again. Has this happened in it has happened in this class that suddenly you couldn't hear me anymore, right? Yeah. Yeah. It happened in another class yesterday, I think it was, or Monday it may have been. And it's so frustrating because everything will be working fine and suddenly it doesn't. In my first class this morning, Zoom would not come on. The internet was good, everything was good, Zoom would not come on. I had the whole class set up, everything done, had to shut every piece of it down and turn off the computer, turn it back on and bring it all back up. It wasted at least 10 minutes of the class. Here's what the thing, I've noticed this before. Sometimes when that happens, Microsoft is trying to load an update. And it seems like every time they do that, it screws something up. Even though I'm not loading it at the time, it wants to load it so it shuts everything down. Or it makes it so it doesn't work anymore. Now, that doesn't make any sense to me, but it seems to be the reality. Okay. So anyway, enough talking. I guess let's pick up where we left off last time. Any questions or anything first? Yeah, I have a few comments. Okay. This obviously one of my best classes of all time, and I'm trying to think how many research papers are in. Let's see. There may be some in this stack I haven't graded yet, but there sure aren't many. In fact, I'm almost about to say none. Have any of you turned in a research paper? Okay, I was afraid of that, so I don't think I've got a single one out of 20. Okay, guess what? This is your last weekend coming up to work on that paper if you work on weekends. Yuck, I can't get Caitlin in. Here she comes. Caitlin's here. Okay. Now, in addition to that, first labs. I'd say probably half of you have turned in the first labs, probably everybody here now. Don't know that for sure. First test, most of the people have turned in the first test. There are some that have not. Here's Don's here. So I guess I need to take talking a while and let more people show up. Okay. Second lab, whoa, only a handful. Look at maybe 6 people have turned in the second lab. Second test, a lot better, but still missing quite a few second tests. Third lab, I finally got 4 of those in at least, so good way to go. Start getting those in, people. Test 3, not quite half of the people have turned in test 3. Lab 4, looks like only 4 people have turned in lab 4. Okay, test 4, I'm not sure, but maybe only 1 has turned in test 4, maybe a couple more. I have several here that I haven't finished grading yet, so I may have some in there, but not this many. Lab 5, whoa, 2 or 3. Oh, Caitlin's trying to get in. She must be having difficulty, because I already let her in once, but she must be having difficulty getting in. Okay, where was I? Lab 5, I think I've only got maybe 2 or 3 of those in. Test 5, 3 or 4 of those in. Lab 6, only a couple. And of course test 6, I just gave it out last time, so those should be coming in sometime. So please folks, this is the last weekend. That means I got to have some stuff. Because next week, here's what we're going to be doing. Today, we're going to finish, or I hope we'll finish chapter 23. I think we will. I don't think we'll finish in time enough to do the lab for chapter 23. Okay, so today's going to be one of those marathons. Okay, because we've been having a lot of labs very frequently and been short on classes. Today we make up for that and have a long class with no lab. I know y'all are excited. I can see Valerie's smiling like crazy now. Okay, looking forward to a long class. Okay, but then on Monday of next week, we will continue in chapter 24. Hopefully we'll get started on it today, and then stop at 4:15 and have the lab for chapter 23. I started working on it and have it written out, but I don't have it typed in yet. So I don't have a lot of time, but I'm going to try to get that done. Okay, so that'll be Monday. So hopefully then on Wednesday we can finish chapter 24 and do the chapter 24 lab. And by the way, I'll give you the chapter 23 test. If we finish 23 today, I'll try to get you the test today. You won't have the lab until Monday, but I'll try to get you the test today so you can work on that. And then the next week we will, on Monday we'll do 23 lab. Hopefully make great progress on 24. And then on Wednesday, hopefully finish chapter 24, do the 24 lab. That's an easy lab. Now you will need your books. So by all means, if you've got a book, get that book and have it with you on Wednesday, because the Wednesday's lab comes right out of the book. Okay, you can do it on the internet, but it's way easier to use the book. Okay, and then wherever we end on Wednesday, that's it. And I'll be giving you both the chapter 24 test, which I think you'll find is pretty easy. This is Nikaya coming in. Okay, and hopefully she'll be here soon. And then I'll also be giving you the final exam. Final exam is very easy, very short. You'll probably be able to do it within a half an hour. Okay, you can take longer, you can take all the time you want, but here's the thing, folks. I would like, okay, you don't have everything today. For instance, you don't have anything for chapter 23, but you have everything before chapter 23. So if at all possible, have everything that you have right now, your research paper, all your labs, all your tests. If you could get them into me today, tomorrow, Friday, Saturday, or Sunday, okay, please get them into me, okay, because Monday, I'll actually give you the chapter 23 test today, but you're not expected to get that done that quickly, but you'll have it. But Monday we'll have chapter 23 lab. We'll proceed on 24. Then on Wednesday we'll finish 24, hopefully get the lab done, and then I'll give you the test and the final on Wednesday. Because on Wednesday, then you'll have, hopefully you have gotten me the chapter 23 test by then, maybe even gotten me 23 lab by then, and then so Wednesday you'll have the 24 test, 24 lab, 24 test, and final exam, and you need to get that to me because technically they say Thursday is the final exam day. That's a weird thing to say, but that's what they're saying. We don't meet on Thursday, so try to get me things in on by Thursday, Friday, Saturday, this is of next week now, or Sunday. Please get me everything you can. Don't wait and turn it all in at once. If you finish something, get it to me, okay? Don't wait and say, okay, I'll just send them all 4 things Sunday night. No, don't do that to me, because then I have to get it all graded, and grades are due in by noon on Monday. So please get me the things as soon as you finish them, okay? This is next week's stuff. This week's stuff, yeah, get them to me as soon as you finish too. Everything from the first of the term, get it to me as soon as you finish it, okay? And then, so get me everything by Sunday evening. This is next Sunday evening, a week from this coming Sunday. Have everything to me. Get as much as you can to me Wednesday, Thursday, Friday, or Saturday, or Sunday, anytime you can, because I'm going to be grading like crazy all weekend trying to get everything caught up. Because grades are due in by noon on Monday. And if I don't have everything from yours by noon on Monday, you're getting incomplete. Now, as soon as you get me the stuff, I'll change the incomplete to a grade, but please get it to me as soon as you can. All right. Any questions on that? Now, if I hear differently, if they give us another day or two, I'll let you know that. But the last I heard, that's what they were planning to do, and that's awfully rushed. It is incredibly rushed. Okay? So, you see what's happened here, if you haven't realized it yet, summer term is supposed to be a 10-week term. But because we're changing from the old operating system we had, which was called Alliant, you probably never realized it, but that's what Student Suite was based on and all that kind of stuff. You know, Student Suite is no longer. Everything is now My Lawson. And My Lawson is based on a new package called Banner. Okay? Everything has to change the Banner before the end of the month. So that's why they're forcing us to have the grades in by Monday week. Because if they're not in by then, we can't get it on the system because that's all Alliance stuff. And then starting the 1st of August, everything is Banner. We won't be able to do anything. I will be able to do a grade change somehow, but they haven't told us how that's going to happen. But I'm sure it's going to be doable. But please, folks, get everything you can in to me, because otherwise we get into a really nasty pinch there. Okay, any questions? All right. Now, I know we started this slide last time, so I don't want to repeat any more of it than I need to. And remember, I complained about, I can't advance this until I click on the slide and then it advances. Okay. I complained about these graphs. I can't tell what they're talking about here. I don't know if you're looking down at a warm air mass and a cold air mass. That doesn't really make too much sense, but it could. That could be it. And then the warm air pushes into the cold air, making a cold front going this way, a warm front going this way. This could be what it's meaning here. And then you start getting, because the warm air is pushing in, the cold air is swooping around, you get circulation going. And that's what they mean by an occluded front. And I think I read you that definition from the text, which they do a terrible job describing. They don't even mention it here, except on the slide right up here. And they say here, an occluded front is one that has been lifted completely off the ground into the atmosphere. The disturbance is now a cyclonic storm. And that's what this represents. Now, that doesn't mean a cyclone or a tornado. It's just any kind of storm that has circular motion. Okay? That could be a thunderstorm, as Roy said last time, a supercell. That's certainly a cyclonic storm, but it's not a tornado. Okay? It's just on a much bigger area and not the intensity. And I think where I left off last time was talking about this. When you have that low pressure area with inflowing upwardly forced winds, that's what's happening here. I was about to tell you about the Coriolis effect. Now, the Coriolis effect is an interesting thing, and here's part of where it comes from. Okay? I don't know if any of you are old World War II buffs, if you've studied those, read about them and stuff. But World War II was the first major war in which bombers did a whole lot of the damage, a lot of the action. We had very high, oops, here comes Scott. Oh, I'm trying to get him in. Okay, there we go. Scott's coming in. Okay. I don't know if you've ever done this, but when you're dropping a bomb from a from a very, very, very high level, it's falling through the atmosphere. Okay? But think about this. The Earth is spinning as it falls. And as it does, that creates a torque. And that makes a twisting action. So just because you're up there in a plane and you look like you're over the target, if you drop the bomb then, it's not going to hit it at all, because you're moving, it's moving, the Earth is moving, all sorts of things are moving, and the odds are you're not going to be nowhere close. So they have to take into account all this. Now, the Coriolis effect, a bomb going down would be high pressure going down. It's going to deviate from straight down in a circular pattern, in a clockwise pattern in the northern hemisphere, counterclockwise in the southern hemisphere. Now, Coriolis effect is because of that. You have the downward movement or upward movement. In this case, it's upward movement, but either down or up, it doesn't matter. Downward movement, upward movement with the spin of the Earth that creates a twist. That's called a torque, by the way. And that's what Coriolis effect is. I can almost guarantee you that every one of you have witnessed the Coriolis effect. Does anyone have a clue of what I'm talking about? Okay. Yeah, Roy, you do? Okay, no, you don't. I think Don has his microphone on. I'm not sure he realizes he does, because I hear some talking in the background, and his is the only one lit up. Yeah, sorry about that. Okay, Don, you realize your microphone's on? Ah, good, you got it off, thanks. There was noise in the background there. Okay. Have any of you ever pulled the plug on a sink of water, a bathtub, or anything else? What do you notice when the water's going out? It's spinning. You're absolutely right. I was going to say flushing a toilet, but I thought that might be a little gross, but it happens there too. That is exactly what we're talking about here. You have a low pressure area. Now, there is not upward force winds, but downward flowing water. Okay, low pressure area. Okay, and when the water is moving downward, you see that spinning happen. That's the Coriolis effect. Okay, now some of your toilets, I know they spray the water around the sides, but when you pull the plug on the sink or a bathtub, there's no spinning going on. I mean, nothing is causing the spinning except the spinning of the Earth. That's what's causing it. Okay, now here is what I consider a dumb story, but it was absolutely true. I had a physics professor at Georgia Tech. He was a honcho in his area. His major area was crystallography, okay? And he was one of the major editors, I think the editor-in-chief of the major international crystallography journal. He was a honcho, okay? And as such, and most of these big scientific organizations like that will typically, not now during COVID, but before, they used to have meetings. Sometimes it may be only every 3 years or every other year. Some of the bigger organizations maybe every year. And one year, the International Crystallographer Association, whatever it was called, I don't know the name of it, they had decided to meet in Buenos Aires. Wait, am I saying it right? No, Rio de Janeiro, Brazil. Now, have any of you ever heard of Rio de Janeiro, Brazil? It's not the largest city in Brazil. Sao Paulo is the largest city. But Sao Paulo is sort of the business capital of Brazil. It's also big on government too, but mostly on business. Rio, though, is right on the beach, and it is the party city of the Southern Hemisphere. Now, at least that's what they claim. I bet you some of the Australian cities would say, hey, they can give them a good run for their money. But supposedly Rio is quite a party city. Okay? And here was, I can't remember his name was, my professor was, had these meetings because he was editor-in-chief of the journal. He had to be at the meetings, of course. And here he was so looking forward to going to that meeting in Rio de Janeiro. Okay? And we thought, yeah, we bet you were. You know, he was telling us the story. And we were just thinking that to ourselves. Yeah, you must have been ready for a big time party city, huh? He said, yeah, I just couldn't wait. When I got to my motel room, I threw down my bags, rushed into the bathroom, and flushed the toilet. Why? He was excited to see the water flow in the opposite direction. Because in the southern hemisphere, the torque is exactly opposite it is in the northern hemisphere. So here he was in the party city of the southern hemisphere and looking forward to flushing the toilet. Okay? He told us the story and we all went, yeah, right, buddy. Okay. But anyway, that's the Coriolis effect. Now, similarly, high pressure area then will produce in the northern hemisphere clockwise winds. Okay, because now with high pressure you have the winds, the air sinks. That's what creates the high pressure. So you have downward movement with the spin of the earth, and that creates a clockwise flow. Okay, now we looked at the weather maps last time, I'm pretty sure, and this one that you see here, this is a low pressure center. Notice the air is moving counterclockwise, opposite the way the clock hand turns. And that's what happens in low pressure areas. That's what happens in a tornado. That's what happens in a hurricane. These big weather producers are low pressure centers. High pressure, you're probably going to have plenty of sunshine coming your way. You know, it's probably very little wind, and in the summertime that can be oppressively hot. Okay, but in the low pressure areas you usually have more clouds. You could have more wind if it's a really strong low, and you could definitely have thunderstorms. So that's what we mean by waves and cyclones. Okay, it will not advance, so let me see if I can advance. Okay, now here is a picture, an illustration of some of the, and this is in your text on figure 2313 on page 583 if you got the big book, 23-11 for the smaller one. Okay, this shows the cyclonic storms. Think this could be major thunderstorm. This is typically how they track or have historically tracked. or you can actually think more specifically tornado tracks. Okay, principal storm tracks across the continental U.S. and generally in the easterly direction, and this makes it possible to predict where the low pressure storm might move next. And I'll give you just a few examples of that. Low pressure areas coming out of the Gulf, they tend to go like this. They usually don't affect us that much unless they are a major hurricane, and who knows what they're going to do. Okay? This track, though, is the one that was followed pretty closely by those storms of, what was it, 2011? That big day we had. They came out of Mississippi, central Mississippi, but they were all up and down the border of Alabama. There were some up here in Hacklesburg and a couple of other towns up here through central, went through Tuscaloosa. There were other tornadoes further down. I mean, they were all up and down the state, okay? And they left the state and made their way on north. Now, here's what happened to them. I think they got caught on this track typically gets caught on the Appalachian Mountains and rides up the westward slopes of the Appalachians and go on out to sea. Now, these are not necessarily tornadoes. They can be, but they're any of your cyclonic storms. Those that go through Oklahoma usually follow this pattern, okay? And for some reason, they find their way across the Appalachians here in West Virginia and go out. Now, this is just generalization. They can do all sorts of variation from this. Those that come through Kansas come through either like this or that, and they're big on tornadoes there too. And Missouri has had several big ones. In fact, it was only like a month or two after our major ones back in April of 2011, Missouri got whammed by more really big storms. Not as many as we did, not as powerful as we did, but they got hit and hit badly. Okay, and those track on over here. Others, a little maybe less common, go up like this. And the further north you get, the less major they are. They can still be cyclonic storms, meaning thunderstorms and stuff, but not as often do they form major tornado tracks. But that's just the general patterns, just about always west to east, because we're in the temperate regions. We'll be seeing this next time actually a little bit later when we talk about climate in this chapter. Okay, any questions on waves and cyclones? All right. I can't think that there's another. I think the slide that's supposed to be here that must not have made it here would be the one that looks like this. Well, let me see if I can, there it is. Okay. You see when you have one of these is low and one is high. I'm looking at them backwards, so I'm having trouble reading them. So let me get it down so I can read it better. If you got your book, it's on the same page, 583 or 23-11. A high pressure center is high pressure because the air is falling, and when it falls, the Coriolis effect creates clockwise flow. The low pressure area, because it's sucking up, because it's low pressure, sucking air up into the column, then that creates counterclockwise flow. And that's usually when you have your major storms. The high pressure is bringing down air from up high, which usually isn't very strong, heavy in moisture or anything else. It's bringing it down and it circulates clockwise, if I can get my clock going in the right direction. Whereas a low pressure area sucks air from around it, which means more moist air sucks it up, and that's an unstable situation, as we talked about earlier in the chapter. Okay? I think that's the slide that should have been here. They must not have gotten it in here in place. So let's now move to major storms. Now this starts back on the previous page, 582 or 23-10. What a major storm is a rapid, violent weather change. Okay? You can have storms that are great. Oh, wait, here comes Thomas. Okay, let's let Thomas in. All right, turning out to be a decent crowd today so far. I hope more people will be showing up. Rapid, violent weather changes, major storms. Doesn't really look much like one today, but I can imagine days when it's hot, it's humid, it's sort of still, and you think, oh, what a miserable day. And then all of a sudden, wham, here comes the thunderstorm. That was actually a perfect setup for a thunderstorm, often associated with a frontal passage. Hot, humid Gulf air sitting over us, humidity's high, temperature's high, here comes a cold front. Now, it's not a cold front, but it's just much colder than what we have. It rises over the top. Now you have, or plows into the warm air, forcing the warm air up over the top. You get the circular flow. There's your storm. So, three major types. The thunderstorm. Now, you might say that's the weakest. Yeah, but there's a lot more of them. Probably more people are killed by thunderstorms than they are by tornadoes and hurricanes combined. I can't quote you the numbers or anything. The fact is, there's just so many more of them. Anytime you have thunder, you have lightning. And sometimes that creates some bad situations. So we'll talk about these each one. Then we have tornadoes. Now, tornadoes are unique because they are the most concentrated, most powerful at the point where they hit, but they've hit a very small area, usually. Hurricanes, however, though they're not as intense, they cover so much bigger area and do way more total damage. Not more intense. Tornadoes are the most intense. Thunderstorms are the most frequent. Hurricanes, they're the biggest. So all three of them have points of superlative nature. Let's hit them one at a time, if I can get my slide to advance. Okay, let's start with thunderstorms. Usually they develop in what I was just describing, warm, very moist, unstable air. Okay? Three stages for these. First, they call the cumulus stage, and that's when the cumulus clouds, those are those great big monster clouds, form. These are associated with convection. Convection is when warm air rises, okay, especially when it has encountered some type of a barrier. The barrier may have been a mountain range where it's very cold. That warm air climbs the mountain and creates a storm, okay? It could have been a cold front, like I was describing before. The cold front comes barreling down, forces that air up. There is your cumulus stage, okay? Now, during the cumulus stage, it's convective flow. Warm air is drug up, and as it dragged up, you tend to get the counterclockwise flow like we were talking about. This is a low pressure area. In its mature stage, all that warm moist air that's been sucked up way high. Look at this, the altitude. This is in kilometers. That's going up to 8 kilometers, almost 9 kilometers high. That would be like 4, almost 5 miles up there. This warm moist air is being drug up. It's way cooler up there. And now that warm moist air can't hold its moisture any longer. Okay? So the updraft in the mature stage can no longer support, because on its way up, that moisture is changing to, remember we said this last time, to ice crystals. Not water droplets. They were water droplets when they were here, but they become ice crystals as they go up. And then they hit more moist air and they go bigger and fatter and heavier, and after a while the updraft can't support them much longer, and they fall. That falling frozen water melts on its way down as it gets warmer, becomes rain. That's the rain we get here. And that's why it feels so cool and refreshing, because it was not long ago, like just a few minutes ago, was an ice crystal, okay? And it is falling as rain now, okay? Now, if there's such a strong updraft that these get carried further and further up before they get heavy enough, there's such a draft upward that's keeping them up there, before they finally get heavy enough to fall, they don't all melt before they fall, and that's what forms hail. Those are the super cyclonic storms, supercells. I was trying to think of the term Roy used, supercells, okay, when you get hail. And I tell you what, snow, it's all right. The roads get slick. We don't know how to drive in it. It's a bother, but we can handle it. Rain, yeah, sometimes it rains too hard, but I don't mind rain that much. But you know what? I really don't like hail at all, because hail happens mostly in the spring, early summer, and every time it happens, I think, oh no, I hope it doesn't hurt the peach crop, because I love my peaches in the summertime, and that hail can really do damage. It can do damage to any crops, because usually your crops are just forming in the spring and early summer, and it has wiped out before wheat harvest. When I was living on the farm in Georgia, it's wiped out peach crops. It's usually strawberries are okay because they come along earlier before you get major hailstorms. But so many of your crops can be damaged, and then that's not to mention your car roofs, your house roofs, and things like this. They can get torn up by hail. I mean, they can do a lot of damage. But boy, you can replace a car roof, but you can't. Don't want to go a summer without peaches, so I want the peach crop to make it. Okay, so finally that's happening, and that's when you get all the precipitation, and you can have severe winds now because of that heavy counterclockwise flow. All that's going on. And finally, all the updrafts are exhausted, and now the big old tall cumulus clouds, they just dump. They empty themselves out, not maybe completely, but lots of it, and you just get rain. All the updrafts are exhausted, and now the rains happen. Usually by this time the lightning's over with, most of it anyway. That means the thunder's mostly over with. The hail, of course, is long since passed if you had any. It's just raining. And now sometimes they're still moving and could be moving rapidly, or sometimes they're fairly stationary and just dump on you for hours. But that's the final stage of your thunderstorm. Any questions about thunderstorms? Okay, as I already said, if there's thunder, that means there's lightning. Okay, so that's what we're going to hit next. Lightning and thunder. Say that again. I thought Thomas said something. Maybe his mic was on by mistake. Okay. Okay, Thomas, are you talking to me or someone else? Oh, I'm sorry. Okay, good. I was going to think I can't make a context out of that. Okay. All right. So let's talk about lightning and thunder. Okay. Remember, you have updrafts. The warm moist air is being dragged upward. You also have downdrafts when the rains and the other things are coming. So you have air columns that are passing each other, sometimes at pretty high rates of speed, and you have the circular motion, usually counterclockwise motion, so you have all sorts of air molecules bumping into air molecules. When that happens, usually electrons get knocked off, and I don't know why they do, but you have some areas that build up negative charges, and where the electrons have been bumped off, those other areas are positively charged. So now you have two charge centers, negatively charged over here, positive charge over here. If those charge centers get big enough electrical potential difference between them, then the electrons, excess electrons here, fire and go into the positive centers because those are deficient in electrons. That's what a lightning strike is. Now that what I just described was a cloud-to-cloud lightning strike. You can also have a large center of electrical charge here, negative charge, electrons, excess electrons, over the earth, and maybe that cloud sinks until it's close enough that now it discharges into the earth. That's called cloud-to-ground lightning. Or you could have had that positive charge cloud, the one that lost a bunch of electrons. It gets too close to the earth, and now the earth by comparison has excess electrons more than the cloud does, so now the electrons shoot from the ground to the cloud, and that's actually called ground to cloud lightning. I don't know if you realize lightning can go in that direction too. Is there any difference? No, they all can kill you. Now, usually cloud to cloud won't normally because it's up in the air, but it doesn't matter which way the lightning's going, it can fry you. Okay, it really can. The charges do accumulate in different parts of the thunder head. One positive, one negative, one positive. It doesn't matter. And what lightning is when you have discharge between the charge centers, where they're cloud to cloud, cloud to ground, ground to cloud, okay? Whatever, when you have those discharges, okay? Now, the discharge can be, like I just said, cloud to ground, ground to cloud, or cloud to cloud. Now, that's lightning. Now, let me tell you, that's a lot of charge with a lot of energy. And I mean, it's pure, almost pure energy. And when it does discharge, it does incredible heating of the air right around it, because this is intense amounts of charge, huge amounts. If you can see that lightning strike up there, whether you can or not, but if you can see it, that's an enormous amount of electricity. Think of the spark in your spark plug that ignites your engine. You can hardly see that little thing, and yet that can set your gasoline on fire in your piston. That's what drives your car, right? Well, guess what? That huge one that you see up there, that huge spark that you see, that is heating things like crazy, especially warm, moist air. It's suddenly expanding that, and then when the charge goes through, that collapses again. Well, that forms thunder. That pressure wave from the expansion and then the collapse, that is a sound wave. Okay? The expanding pressure wave from the heated air produces the crack of thunder. Now, some people will claim otherwise, and they have names for it. But if you can see lightning, even if you don't hear the thunder, that means that lightning was so far away, but big enough for you to see, it thundered somewhere. Where that was, it did thunder. Even if you don't hear it, that doesn't mean it didn't thunder. So you cannot have lightning without thunder. But then on the other hand, you cannot have thunder unless there's been lightning somewhere. Now, I've heard people talk about heat lightning, okay, as if there's no thunder with it. There's thunder, okay? There's going to be thunder. Or, and sometimes they'll say, oh, you hear the thunder and say, well, that's just heat lightning. There really wasn't any lightning. No, there was. If there is thunder somewhere or another, you may not have seen it. It may have been on the other side of the clouds. It may have been, below the horizon, but somewhere it lightning. Had to have. You can't have one without the other. Now, let me give you a couple of stories here. I'll try to make them fairly quick. There was one night when I was in the Navy, I don't remember which dog watch it was. It was one of the dog watches. What they had in the Navy, you had 4-hour watches. I'll start uh, at uh, let's start at 8 o'clock at night. Okay, that watch was 8 to 12, and then the mid watch from 12 to 4, and then the morning watch was from 4 to 8, and then the late morning watch was 8 to 12, and then you had the afternoon watch that was 12 to 4. But then you had what they called the dog watch, because people had to eat supper. You could eat supper between those people going on watch ate early before their breakfast early before they relieved at 8, and the people coming off watch ate their breakfast late, when they got in after 8. Okay, same thing at lunch. People going on watch ate their lunch early so they could be on watch on time. People coming off watch ate their lunch a little late. Okay, that happened. But in the evening meal that was served around 6, that's right in the middle of a watch. So we had a 2-hour watch from 4 to 6, and then a 2-hour watch afterwards. So you got to eat lunch before 6 or after supper before 6 or after 6. Well, it was one of those dog watches. I went up and I had the watch on the bridge, and I went out there, and I don't know if it was going on when I first got there or if it started after I got there, but we had the most magnificent display of cloud-to-cloud lightning I've ever seen in my life. It looked like a network, just constant. It looked like the whole sky was nothing but a spider web of lightning, just strike after strike after strike, and not just a single strike, little strikes just covering the whole sky, off and on, greater or lesser, and almost for 2 hours. And none of it was hitting the ground. None of it wasn't coming down. We stood out there and watched that. It wasn't even raining at the time. We stood out there and watched that lightning and were just fascinated with it. I've never seen a display like that before. A lot of cloud-to-cloud lightning. Okay. And this one, I've just seen pictures of this. I've seen pictures where someone had their camera right about the time of the thunderstorm and just happened to take the picture, and you would see the lightning go from the ground to the cloud. It caught it midway up and you went, my word, it does happen. You heard about it happening, but you just never thought it did. You see that lightning go up from the ground to the cloud. It happens real quickly, and it just happened to be his shutter opened it right the time it was halfway up, right at the ground, and losing brightness as it went up. It was amazing. Okay. But anyway, so you can have them both. Okay. Now, here's the illustration of this. In that big cumulus cloud where remember you have updrafts. Yeah, get back here. You have updrafts of warm moisture air going up, downdrafts when the rain is coming down and bringing cooler air down. They're bumping against each other, and you could have excess positive charges here, excess negative charges here, excess positive charges here. Up here you have cloud-to-cloud lightning. Down here you could have cloud-to-cloud lightning. But here you could have ground-to-cloud lightning. Now, you might say, but wait, the Earth is neutral. Ground is neutral. Well, not necessarily. If you have a cloud close enough to the ground and it's positively charged, it's going to attract negative charges from the ground, and they separate by what they call polarization. Okay? The negative charges come up and the positive charges are trying to get away from these positive charges. So you set up your potential difference there. Now, don't worry about the rain. That's immaterial where the rain is. But this could be discharging. And this is actually from the ground to the cloud, because it's actually the negative charges, the electrons, that are moving up in lightning. Here is cloud to ground lightning, because your excess electrons here, again, attract the positive charges from the Earth and push away, repel the negative charges. Then your potential difference gets great enough, and then these discharge downward. Or, if these two clouds are close enough together, here's another chance of cloud to cloud lightning. The negatives from here will jump over to the positives from there. And some way, negatives here to positive there, negative here to positive there. Or you could have your same setup as you had here, ground to cloud or cloud to ground. Okay, that's what happens with lightning and thunder. And usually these big storms that are circulating widely like that, they're creating enough friction between the air molecules, you do separate charges. And when you separate charges, how they discharge that excess charge is by lightning. Okay. The next, and this is a big one in our neighborhood in recent years anyway. I can remember when I was growing up, we always thought of tornadoes as being out in Oklahoma or somewhere in the Midwest, Kansas, places like that. And they did have lightning track through, and they were big and they were violent. But the main thing there is there's nothing to stop them because the Great Plains, there's no trees, there's no hills, there's nothing to stop those from moving across. And that's what made them so devastating. But boy, in the last few years, it didn't matter how many trees or hills or even mountain ranges were in the way. These tornadoes just came ripping through and just seemed to keep the energy sucking in. And these are the smallest of these storms, but they're the most violent where they're happening. In that small area where they're happening, they're the most violent. They have the strongest winds, and they didn't do the most damage right there. Okay. It's a rapidly whirling column of air. The diameter, they say, can be between 100 meters and 400 meters. Now, 100 meters is a little bit longer than a football field. That would be like one end zone to the next goal line. Okay, about 100 meters. 100 yards would be goal line to goal line. 100 meters a little bit longer, so it would be closer to an end zone to a goal line. Okay, opposite goal line. Up to 400 meters. Now you're getting close to a mile in diameter. That is a big tornado. Now, back in 2011, I'm pretty sure the one that ripped through Tuscaloosa was probably more than a mile wide. The one that hit Hackleburg, wherever that is, I don't know where it is, but I saw the pictures of that. That looked to be more than a mile wide. I mean, there were some monsters that day. I mean, huge. The wind speeds up to 480 kilometers per hour. Now, in terms of miles, that would be something on the neighborhood of 250 to 300 miles per hour. Oh my word, that is wind. Okay, the damage produced by those high winds, that's one thing. The drop in pressure, that's another big thing that people don't realize at the center. And then, of course, the flying debris caused by the high winds. Okay, now, have you ever heard of a tornado caving in the roof of a house or a building? Probably not. What a tornado does is sucks off the roof of a building, okay? Because of that low pressure. It actually pulls the shingles up. It pulls the roof up, okay? It sometimes takes a whole house off of its foundation. It lifts it, twists it, whatever. That's what happens. It's not pushing it around, it's lifting it off, okay, because of that drop in pressure, okay? Now, the flying debris, the winds at that kind of speed, they pick up. Now, I don't know if anyone saw the movie, what was the name of that movie? Was it Twisters, that's it. They had the cows flying in the air. Now, I don't know if I bet you that can happen, but that's just not that common. But there are times when cars have been lifted off the air and thrown into something. Okay, and cars are probably heavier than cows, so I'm sure it's happened with cows too. Cows usually have enough sense to get down out of the path, but Twister showed the cows flying around. It seems like I never saw the movie, but I saw the previews, and that was happening. The flying debris can cause lots of damage. Now that does come through windows and come inside, but generally, when you have a tornado, the glass is blown outward, is sucked outward, not blown inward. Only when a limb or something like that comes through a window do you have glass coming inside. But that's because of the wind. The pressure actually sucks the windows out, and the glass moves outward, not inward. Okay. Now these are usually associated with really intense thunderstorms. Okay. Now, here is a picture of one. Your book has a picture of I don't know if it's the same one, just a closer shot. The one in the book says this one was photographed 9 miles west of Marquette, Kansas. Like I said, they've had some major ones, and they're flat out there, so those can go over large areas. It seems like before, when I was in the book that had this picture, it seems like this may have been near Dallas, Texas. I just don't remember for sure. But those are, you don't want to see that. You don't want to be close to that. Okay? Now, that's all they say about tornadoes. Do any of you have any stories about it you wanted to share? I know that when we have gone to the Channel 13 Weather Center, I've heard Jerry Tracy tell this story more than once. This was not the set of tornadoes on 2011, okay, in April 2011. This was a few years before that, when there was a really major tornado that came through. I know one wiped out, wasn't there a town with Oak in its name? Oak Grove, yeah, Oak Grove. Didn't they have a really bad tornado come through there? Say again? And now Pleasant Grove had the tornadoes happening in 2011. Oak Grove, I think, had them like 2, 3, 4 years before that. Yes, I think so. I believe it was. That would have been back around what, 2006, 7, 8? No, it may have been earlier than that, because I think we were still Bessemer State Technical College. I was teaching an evening class. It was a 5:30 class. We had just gotten started, maybe 15, 20 minutes, when we heard the weather thing go off, and I looked outside. There was windows in my classroom. It was one of the stillest days I've ever seen in my life. Not a leaf was moving. And I had a maple tree right outside the window. Not a leaf was moving on it. I said, that must be a test or a mistake or something. It's as still as I've ever seen it. A few minutes later, the night coordinator at the time, and his name was Dennis Wynn, came up and said, "Get downstairs." He said, "There's a major tornado in the area." Actually what was happening, it sucked all the energy to that area, McDonald, Chapel, Oak Grove, those kind of areas, and that's why there's not a bit of wind outside where we were. It really didn't come anywhere close to us at the school, at the college at the time. It actually came closer to our home. It went near the airport, but it lifted before it got to the airport and went over the airport, and we lived just a few miles south of the airport. So it was really, really intense. But I think Jerry Tracy told this story that it just seemed like a very normal day, just like I was describing. And this woman happened to, I can't remember how the story went. He told it. It seems like a neighbor called her and said, she had turned off her TV. She didn't have her weather thing on. And I don't know if they were close enough to hear the siren or not. It was somewhere out, in a sort of a remote area. But a neighbor called her and said, "Have you heard?" She said, "Heard what?" "There's a tornado in the area." And the woman went out and looked on her porch, and she could see it from where she was. And she was in a house with a crawl space, no basement. And she had heard go to the lowest area, and there was this one entrance to the crawl space that you could crawl under the house to, do whatever you needed to do. And she decided to crawl under there. She got just about halfway under when the tornado came by. She happened to grab her arms around a pylon, a support structure there, wrap her arms around that support structure because it was trying to pull her out. Literally. It took her shoes off and one of her socks off. She was lying there with her feet sticking out and just hanging on for dear life. And then it passed. She never found her either shoe or that one sock. They were taken off and they went. And that's what you see here. What you're seeing there is dust and debris that's being sucked up by the tornado. When it first starts, you don't necessarily see that, but it's just as strong. But after it's run just a little while, it's sucking all that stuff up. Low pressure, intensely low pressure, pulling that stuff up and rotating like crazy in a counterclockwise direction. That's a tornado. So what's a hurricane? Well, a hurricane starts as a low pressure area, an area of low pressure, but usually pretty mild low pressure. Now remember back when we were talking about in that range between 10 degrees south of the equator and 10 degrees north of the equator, the air is the most direct heating from the sun, so it goes up and you have a band of low pressure there. Well, in the hottest part of the summertime, which is right about now, those areas of low pressure can be incredibly get stronger. And when they get strong enough, they're then called a tropical depression because they happen in the tropics, and it's called a tropical depression. It's just an area of low pressure, a lot like a thunderstorm might be here in the temperate area. The winds are generally moving faster than they would at a thunderstorm, something around 55 kilometers per hour, which would be maybe around 30 miles per hour. That's still pretty high wind, but it's not enough to do tremendous amount of damage, but it would do some. But as the pressure drops, the wind speed increases. So then it may develop into a tropical storm. This is more intense low pressure area, okay, and the winds now move up to in the 56 to 120 kilometer per hour, which would be, like I said, around I was just doing the math in my head, about 35 miles per hour up to 72 miles per hour, something around in there. That's a tropical storm. But if it gets more and more low pressure, more and more twisting of the air, the lower the pressure, the more rapidly the wind is blowing. And when it does anything in excess of that, or I think they usually use around 75 miles per hour, that's when it becomes a hurricane. Now, they have different classes of hurricanes, just like they have, classes of tornadoes. And I forgot to mention that. I think they'll mention that for hurricanes. They skipped over the tornado damage. So when we hit the hurricane one, I'll go back and refer to the tornado ones, okay? So I think we'll get there. But the hurricane, when it gets over under a certain pressure, and it's pretty low, and the winds in excess of 75 miles per hour, which is fast on an interstate, it's really fast if it's a sustained winds. The fully developed hurricane has in the middle of it a very calm eye, the eye of the storm. Almost nothing's happening there. It's perfectly calm. You can look out from that. I haven't been there, but I've heard people talk about it, and you see this wall of debris swirling around you. That's the wall of the storm, okay? But in the eye, in the middle of that, you have almost no wind at all. Nothing's going on there. It just seems like a strange day, but just a day. Low pressure, very, very low pressure, okay? Now, another time for another story. I had a good friend. He was an undergrad when I was a grad student at University of Georgia. And he was a forestry major. He liked being outside. He thought that would do it. But after he graduated, he thought, I really love to fly. His dad was a commercial pilot. He had always flown his whole life. He said, I really love to fly. So he went back and he had already flown some because his dad was a pilot, and he got his license. But it was at one of those times when people weren't hiring. It was a depression type time. And so the airlines were laying people off. In fact, they couldn't get it. So here he was, just got his, big license, jet license and stuff like this, and couldn't find a job. His dad was working this was at the time when all the airlines were crumbling and crashing and doing all sorts of things, not literally crashing, but I don't know if y'all remember. There was a time we had Pan American, TWA, Eastern, Ozark. They're just Braniff. There were just all these airlines, and they were all prospering like crazy. And then they crashed. I mean, the market crashed. And his dad worked for Eastern. Eastern folded. I think U.S. Air picked up a lot of what was Eastern. So they started having lots of consolidation. So his dad, I think, lost his job temporarily, but was picked up by another. So sure enough, it was a rough time. Well, he still wanted to fly, and he desperately wanted to fly. Guess what? One of his first jobs was flying. He was a hurricane jumper. He would fly these big planes. They were like passenger airlines, but they were filled with equipment. They took pressures, they took wind speeds, they took humidity levels, they took everything. They were a flying weather station. And what they do would go up and fly over the storm. Still, it had to be incredibly rough with all that delicate equipment. They went way over, but once they got through the wall of the storm, then they came down and flew around in that calm eye. While he did the flying, while the meteorologist on board took all their measurements. And then when they were through, he'd fly up and out. And again, it had to be really rough flying over that eye, over the wall of the storm. So yeah, they do have calm eyes. Sometimes they're miles across, so you could easily have a plane flying around in there. I just wouldn't want to get there and get back, because that's the hard part. Okay. Here's one such storm. The figure 2319, on page 586 or 23-14 shows a satellite observing a hurricane's eye and the counterclockwise flow of the wind. You can see that. You can see it here. You can see the bands twirling around in a counterclockwise direction. Okay? Now, that has significance. Okay? If this hurricane is coming toward you, say you're somewhere down on one of the beaches, okay? Now, let's say this was heading toward Mobile. Let's just imagine that, going toward Mobile. You don't want to be on the eastern side of that storm, because you see the hurricane's moving that way, and the counterclockwise flow is going that way. You are going to encounter an awful lot of wind. On the backside, on the western side of that storm, the hurricane's moving this way, but the wind's moving in the opposite way, so the wind force is still strong, but it's not nearly as strong. But there's that eye, and in the middle of the eye, it's perfectly calm, eerily calm. Okay? Strange but true. This is called the wall of the eye, and that's where the most violent winds are. And they say that from inside the eye, you look at that, and it literally looks like a wall, but it's a wall that's constantly in motion, just things flying past. Okay? But it's actually looks like a physical wall there. Okay. Now, how big can these things be? Like I said, the eye of the storm can be a mile or more across. Just imagine how far out here, 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 and there your danger is. Out here, there's still danger, but boy, in here, you're getting blasted. Okay? Now, here's basically what we're talking about with a hurricane. Now, this is a cutaway side view shot. Okay? Again, it's a low pressure area, but this time's a little different from a thunderstorm. A thunderstorm, the low pressure is sucking air up. Here, the eye of the storm is sucking air down because the low pressure is so intense in here, it's sucking air down, and then that air is getting pulled up into these areas, and that's where the upward flow creates the counterclockwise direction, just like the upward flow in a thunderstorm does, and then a tornado does. This is just so much bigger. Look at the eye there. That looks like about 10 kilometers, to 10 kilometers. That would be about 20 kilometers wide. That would be 12 miles across. The eye could be as big as 12 miles across. Now, the maximum winds and rains and everything else are right here along that wall and just inside the wall. And it would be about from the wall of the eye to the center of this cloud formation you have here. That would be, excuse me, getting really dry. Helps my throat a little bit. And these are all hurricane force winds here. Outside of that, they have what they call gale force winds. That would be of the strength, say, of a tropical storm. Still really, really strong, but those are out here. Okay? Upward flow here, outward flow there, but still really, really strong winds. Okay. Now, I mentioned a hurricane hitting the Gulf Coast. Now, I mentioned Mobile. This one didn't quite hit in Mobile. It hit a little east of Mobile. But I was here back in, we lived in this house. I don't remember what year it was, but when Hurricane Ivan came through. Do any of you remember Ivan? Hurricane Ivan was not one of the really strong ones, but it was strong enough, believe me. It made its way overland from the coast up to Birmingham and was still strong enough to be considered a tropical storm. It had winds 56 to 120 kilometers per hour, which would be basically, what did I figure that to be? 35 to 75 miles per hour wind. Now, we had friends, one friend who lived on, I think, Sapelo Island, maybe one of those islands down there near Mobile. She was doing research down there for, I think, Food and Drug Administration or somebody like that. and they told mandatory evacuation, and she came up to spend it with us, and she found a friend down there who had nowhere to go, so she invited her to come up too. So we had these two people show up, you know, driving, and we welcomed them to come up and sit out the storm here. Well, Carol had a house on that island, but it was on, let's go back to that previous shot, it was on the west side of where the storm hit. Ivan hit over, I don't know, somewhere around, I don't know exactly where, but maybe Watercolor or some of those other towns. It was east, whereas this island was over here in Mobile Bay. It was on the downwind side, the circulation side here, and it got a lot of wind, but they build pretty strong houses there. She found out later her house never lost power. She came up here to Birmingham, and within, I'd say, a half hour of her arrival, well, we live in an area with a lot of trees, and some of those 35 to not quite 75-mile-an-hour winds came through. They knocked out transformers, they knocked out power lines. We were without power for pretty much the whole weekend. We had gas range downstairs, so we did all our cooking on the gas stove top. We had pretty fierce rain. It lost a big limb out of a con tree in the backyard, but that's all we lost to speak of. Lots of little limbs, but it was still a tropical storm after going those hundreds of miles between the shore and us. That's the one I remember the most. I remember when I was young, there was a Hurricane Hazel that went through North Carolina when my parents were living there. It did a lot of damage, and there were others that came through Georgia when I lived there, but I can't remember any as strong as Ivan coming through. Okay. Say again? Uh-huh. And y'all were probably pretty busy too, weren't you? Yeah. Yeah, because lots of people were getting some type of injury because of that. Now, another thing I've heard Jerry Tracy talk about, you've heard the term the storm surge. Okay? I'll tell you what my misconception was. My misconception was, you see all this counterclockwise flow, all this is coming off the Gulf, and I was thinking it was blowing the water into the land here, and that's what created the storm surge. And Jerry said, well, yeah, that's a little bit of it, but it's really not most of it. Most of it is because the intensely low pressure sucks the water up. That's what creates the storm surge, not the winds across the water. It's the low pressure sucking the water up into the storm. Now, this is something I heard about Mobile Bay. I think it was after Ivan. Remember, Ivan was here, Mobile was over here. Now, this is Ivan, but I'm just using this as an example. Mobile was over here somewhere. That storm surge that hit the beach here sucked the water out of Mobile Bay. And they said it went down to a very low level. I think there were areas they said you could have walked across Mobile Bay because that low pressure sucked all the water here, leaving here. Now, we went down to the beach. My wife's family used to go to the beach about every 2 or 3 summers, maybe 3 or 4 summers, something like that. They love going to the beach. I never was a big beach person. But anyway, we went down a few years after Ivan, and they always liked to get shrimp while they were down there. And they said, and so that Karen's dad asked the guy, said, well, did it wipe y'all out? He said, oh yeah, it always does. But he said it was good. He said, because if you don't have a major storm come through like that, the water gets so stagnant and polluted that the shrimp can't do well. You need to come in and wipe out the whole area, wash it clean. Yeah, you lose them all for a year or two, but then when they come back strong. And I think we were down there just as they were coming back, and they got some really great shrimp that year. So Mother Nature knows what she's doing, okay? Now here's the other thing that Jerry Tracy has said. I've heard him say this more than once. Hurricanes are absolutely necessary for us to have life on the planet, because otherwise all that heat and moisture and everything else would pile up in the equator, and it would get unbearably hot and miserable. Nothing could exist if we didn't have these hurricanes that carry all that energy, all that moisture, all that heat, and carry it and dissipate it to the north. In the northern hemisphere, they dissipate it to the south in the southern hemisphere, and that's why they are essential to have to distribute. He said otherwise the polar regions would be way too cold and the tropical regions would be way too hot. He said we have to have the hurricanes to distribute. Now, with global warming going on, that makes the hurricanes, it seems to be making the hurricanes more powerful and more frequent, because you have a greater discrepancy there, so more heat is having to be dragged away and sent north or south. Okay, that's a little soapbox. I'll get off of it. Okay, now we move into weather forecasting. This is section 23.3. How are we doing on time? Okay. This is a tough business, and that's why I really miss the fact that we're missing the opportunity to go to the weather station and you hear the meteorologists talk about what they have to do to try to come up with weather forecasting. Now, think about what our atmosphere is. It covers the entire globe, and it goes miles and miles and miles up. Okay? And you're trying to model that atmosphere. Hey, supercomputers have a hard time doing that. Before we had supercomputers, it was anybody's guess. Basically what they did, they took the average over year after year after year, said this is most likely what's going to happen, and that was about it. Or they'd look a little bit further to the west and see what was happening there and say, it's probably going to happen here tomorrow. So that's what they'd say. But weather forecasting today is based upon mathematical models of an enormous atmosphere. There are literally billions of really complicated calculations that necessitate the use of those supercomputers. And even with that, they can't get it right. Okay? They're only fairly accurate for up to maybe 3 days. So when they put that 7-day planner there, that's more like 7-day wishful thinking. Now, they have some good evidence to base it on, but it's not very accurate more than 3 days. Okay? There could be huge variations before that 4th, 5th, 6th, and 7th day comes along. In fact, it's so far out there, most of the time people forgot what they did. They said it was going to be 4 days ago what it is today, or 7 days ago what it is today. They probably changed it 3 out of the 7 days, since then, back and forth, because they're just not. Here's the major uncertainty. We've got insufficient technology to connect the small scale events to the large scale events. It's just not there. Now here's just a little sample of that. One set of points they try to gather, is a lot of these major weather stations will send up, I think it's only like maybe 2 or 3 times a week, they send up a weather balloon. Okay? And that's a the balloon that carries a load with it, and in that load are some temperature sensors, some wind sensors, some humidity sensors, all the things they can think to measure. And they send these up and go through the atmosphere slowly, and they're taking measurements, sending them, radioing them back to the surface, so everybody collects those data from that one place. And probably the distance between one weather station and another weather station could be hundreds of miles. So here you have just a sample at one time, maybe 3 times a week, of what the temperatures, wind speeds, relative humidity, all that kind of stuff is as they go up through the atmosphere. So that's what they're basing 7 days of forecast on? No. Now, that's not all. A lot of the aircraft, commercial aircraft, military aircraft, other things, have devices on them that collect information and send those automatically. The pilots don't have to worry with it. It's done automatically, sending them to the nearest weather station. So they're getting another sample here where that plane is, one here, one here. So you're getting just these little spot samples here of what's happening on small scale events here, and trying to tie that in with what the big overall pattern is. We don't have the technology to do that, and we don't have the data to do a good job of it. Now, they make a little statement here that's really bizarre, but it's true. Ultimately, oceanic influences need to be better understood. We know more about the moon than we do our own oceans. We know a lot about our oceans, but they're so deep, they're so complex, they have currents, they have all these other things going on. We don't understand them well enough, and they influence the weather in ways we don't even know. Okay, so there's another complicating factor. A huge atmosphere, we only sample very irregularly and not very often, and we're trying to build our models based on those few little samples. And then you have an ocean surrounding us that we don't understand what influences they have on the weather. We know the influences, but we don't understand how, why, when, where, any of that. That finishes the first part of this chapter. Okay, and it's really bizarre because this is under weather forecasting. They don't have a separate topic here. Now we move from weather to climate. And some of what they were talking about back here, small scale to large scale events, that's spatial events. Weather and climate, they differ in time events. Okay, what climate is the composite large weather patterns occurring over a number of years. Weather is what's happening today. The temperature, the wind speed, the relative humidity, the wind direction, that kind of stuff. That's your weather today, and last week, and this week. Local, recent. Climate is what's been happening over years, over decades, over centuries, maybe even millennia, okay, over a number of years. Now, your climate turns out to be your determining factor in all sorts of things. Number one, what types of plants or animals you'll find at a given location. Okay, I'll give you one really bizarre example. Has anyone ever heard of an armadillo? Surely someone has. Of course. Armadillos, back when I would say in grad school, which was many decades ago, they saw the first armadillo they had ever seen in Nebraska, because I happened to be in grad school there. They had always been down in Texas and Mexico. But armadillos are all over the place now. Our house over in Georgia, I still have never seen one, but we've seen the remains of one. the shell and the part of the skeleton, and we've seen holes that they've dug which are enormous, okay? But they didn't used to be in Georgia. When I was young, armadillos were something that lived down in Texas. Maybe Louisiana was as close as they got here. They did not live in Georgia. They did not live in Nebraska. So our climate, it has been a changing. Now here's another one. Armadillos aren't particularly a very positive thing, but here's one that is. We, until just a couple years ago, had beef cattle farm. Okay, my father and uncle had started the farm many decades ago, back when I was about 4 years old. Okay, that long ago, 60 some years ago. Okay, I can remember my dad always worried about all the flies that were getting on the cattle, because sometimes the flies could give them eye infections and other things. So he had these rigs set up to help put a insecticide on the cows when they'd walk under, going to and from the water trough. They go under this thing. He kept it soaked with mild insecticide, but fuel oil, burnt motor oil, something like that, that would stick to the cow's, hide, and that helped control the flies. Well, it seemed like maybe 15 or 20 years ago, it may have been longer now, we started having these big, beautiful, awkward-looking birds called cattle egrets. And they are beautiful when they fly. I mean, they're not quite like a seagull, but they're big, long wingspan, fly. Walking around on the ground, they look as awkward and as anything you've ever seen, but they hung around the cattle all the time, just feasting on the insects. So guess what? We didn't have to worry about the flies anymore. The cattle egrets were just getting their fill of those flies. Okay? Very positive thing. I still love seeing those things fly. When we mow the pastures or the fields where our pine trees are now, they'll sometimes show up because you're stirring up insects. Love to see them. Now, climate is also a determining factor in the types of houses built. Have you ever seen the type of houses they have in the Alps? What do the roofs do? They call them A-frame. Really tight A-frame houses. Why? You want the snow coming off of those. You don't put a flat roof like they have on campus. You don't put a flat roof in the Alps. The snow would come on those and cave them in. Okay? You wouldn't do that. You put steep roofs on in the alpine areas so the snow slides off. Okay? I mentioned before crawl space houses. Very common here in the southeast because we never get enough cold weather, or hardly ever get enough cold weather to freeze below ground level. You'll get frost in the morning. Sometime it may last all day or a day or two, but it always thaws after a few days at most. Okay, so you can build a crawl space house. You don't worry about, most of the time, pipes bursting. However, those rare times it does, I mentioned the Arctic vortex, I think a couple classes ago. Hey, we had pipes burst, okay, because the crawl space area, that cold air came in and burst pipes, okay. Most of the time that doesn't happen here in the southeast. Up in the north, every house has basement because you have to get what they call the stem wall to go down below what they call the frost line. You have to get below that otherwise you're going to be having a lot of burst pipes. Lifestyles, okay? Is there really a lot of hockey played around here? Ice hockey? No, because you don't ever have ponds and lakes that freeze over. Now, I know Atlanta had the Atlanta Flames at one time, and they have had, teams in the South, but they have to make their own ice. Where is it big? Canada. Why is it big in Canada? Every kid in Canada grows up skating on the lakes, in the wintertime. What else have they got to do in the wintertime? So the lifestyle is very different. Where are most of the big swimming schools? Not up north. They're Florida, California, Auburn. They're down here in the south where you can swim almost year round, okay, or at least long periods of time, okay? Lifestyle depend on climate. Now, climate also influences the shape of a landscape. We talked about this before. The places where you have large amounts of moisture, warm temperatures, your mountains and your hills are going to be very rounded then, because all that chemical weathering, all the physical weathering that accompanies the rainfall and the high temperatures, that's going to smooth out your landscapes. Whereas out in the very brutal cold areas, you have jagged mountains and stuff because there's not that much chemical weathering going on there. Types of soil, we talked about this too. Here in the southeast, our soils, topsoil, are usually measured in inches because you can't build up much organic matter. The organic matter dissolves or chemically is decomposed so rapidly. I put out pine straw down we have a hill on the side of our house. I put out pine straw, if not every year, every other year, because it just disappears. It doesn't wash away. It is the warm temperatures, high moisture, the bugs eat it up. Okay, literally, microorganisms are always doing. Up in the Midwest, further north, it gets cold in the wintertime, shuts down chemical activity. Their topsoils, they measure in feet. They don't measure in inches. They measure in feet. Agricultural type and productivity, again, very related to the soil, but here too. Here in the southeast, you can plant winter grains. You can plant them in the late fall. They won't do a lot of growing until maybe around February and March, and then they take off. You harvest those in May or June, and then you can plow those fields up and plant soybeans, and you can double crop. You can get grains in the wintertime, harvest those in the early spring, and then harvest your soybeans in the fall. Double cropping. Up in where the great, wonderful soils are in Iowa, they only have time for one crop a year because it's too cold otherwise. And if they don't get into that field, if it's too wet, too cold, too anything, and they don't get into their fields in time, and they don't get them planted, then they may have such a short growing season that they can't get their harvest. And then the prices go up because they produce a lot of food. So agricultural type and productivity depends or influenced by climate big time. Pecan trees. Great here in the southeast. When I was in Lincoln, Nebraska, I only knew of one pecan tree that produced. Okay, they may have a few that people tried to plant there, just too short a growing season. This one adapted somehow, and one year, maybe every 3 or 4, they actually get a harvest of pecans. Okay, and they loved them. Okay, we would get them just about every year. Okay. Citrus crops, only in the tropical areas. We do lemon trees here, but in the wintertime, we have them on rollers so we can roll into the garage. On nights that get below freezing, we roll them back out in the daytime when it gets above freezing. There's a Satsuma orange, or it's more like a mandarin orange, that will grow around Mobile and a few places. We got one plant, we got it in a planter so we can roll it in the wintertime, roll it out. Haven't gotten any, we've gotten lemons and limes, but we haven't gotten the Satsuma yet. We just got it this year. So climate affects. Cotton has a long growing season. They don't grow cotton up north. They grow it down south. Okra has a long growing season. They don't grow it up north. They grow it down south. So lots of things are like that. Sugar beets, we'd have a hard time growing here. They grow it up in Idaho. Okay. So let's look at some of the major climate groups. This again is on page 588 or 23-16. Two primary factors in the major climate groups. One, the intensity of the incoming solar radiation. Now that's determined by, we live on a globe. A globe is circular. Near the equator of that globe, the incidence angle is very close to 90 degrees. It comes in almost dead end. So how much atmosphere does it go through? Just a few miles of atmosphere, okay? And the atmosphere is what dissipates the energy coming in from the sun. Move on up the curve to where we live in the temperate area. Now the incoming radiation comes in obliquely and has to go through more atmosphere because it's coming in at an angle. And then it doesn't directly hit the surface of the earth, it hits it at an angle, so you don't get nearly the intensity of solar radiation. Up near the polar regions, hey, even in the best time of year, that is coming in through so much atmosphere and at such a low angle, hey, very little solar radiation hits the polar regions. Now, that also influences, so to speak, the number of daylight hours. Near the equator, just about always, they're very close, and we did this in a lab, the second lab. Almost always 12 hours of daylight, 12 hours of darkness, 12 months a year. Very little variation in number of daylight hours. Of course, it's always warm, pretty much, and no reason, okay. However, my wife's family, when they quit going to the beach every 3 to 4 years, they started taking other trips. Maybe not quite that frequently, but other trips. And we went to Canada one year, actually 2 years, I think. Not near each other, but separated by several years. And we happened to be up there in mid to late June, which is near the summer solstice. And in that summer solstice, you think our days were long here? The sun didn't go down in northern Canada until 8:30, 9 o'clock at night. And it was still light even later. It was hard to get a good night's sleep because the next morning it was coming up at 4 o'clock, okay? It was hard to get a good night's sleep just because it got light, stayed light so late. Now, if we'd have been up there in the wintertime, been hard-pressed to find any daylight because it was getting dark maybe at 4 o'clock and then staying dark until 10 the next morning, okay? So, number of daylight hours, okay? Not the same as the intensity of solar radiation, but a lot of the reasons for it are similar. And the reason for that variation is the tilt of the Earth's rotation axis. If we just sat straight up, then everybody would have 12 hours of darkness, 12 hours of daylight, 12 hours year-round. But we're at an angle, so when we're spinning here, up here, if the sun's over here, they have no hours of daylight. Down here, 24 hours of daylight. And in between, around the equator, 12 and 12. And as you go further from the equator, the greater disparity in number of daylight and darkness hours you get. Now, near spring and fall, 12 and 12 again, because the tilt is even with the sun, spinning just along that axis, everybody's 12 and 12. That's in equinox, fall or spring. So, the equatorial regions receive more direct solar radiation. That's what we're talking about here. The intensity changes on a yearly basis. Now, this is a weirdly put together slide. This should be a bullet like that is. That's separate from this, okay? In the equatorial region, the intensity doesn't change on a yearly basis. It's almost the same year-round. In the other areas, like the temperate area, the intensity changes on a yearly basis. And the number of daylight hours varies annually, mostly in the temperate regions. This is not the equatorial region. Equatorial regions, almost always 12 and 12, and the intensity doesn't change much on a yearly basis. So, poorly put together slide. I know what they're trying to say, but they didn't do a good job communicating it. All right, let's move on to climate and latitude. Okay, and this is on page 589 basically, or 2317. Okay, now when they're talking low latitudes, that means small numbers. This is near the equator, the low latitudes, 0 to 23.5, 0 to 10, low latitudes, okay, north or south of the equator. Here you have high solar radiation, comes directly in, you're warm year-round. The yearly variation very small. Their summer to winter, they hardly notice it. Now, I say that what they usually measure is rainy season, dry season. So they call them the monsoon seasons. They don't worry about temperature variation. There's very little of that. What they worry about is rain variation. And that happens for different reasons. Okay? But it's not that they don't have falls, winter, summer, and spring. They still have the same calendars we do. It just doesn't make any difference in their temperature, or very little difference. But their rainfall may vary greatly during month to month. So the temperatures are uniformly high, so really they don't have much of a winter or spring or fall. It's almost summer year-round. Hawaii is the only state in the U.S. that's in the low latitudes, and their average temperature, I think, because they're right on the ocean and it keeps it a little cooler, is right around 80 degrees year-round. My nephew was in the Navy, stationed in Hawaii for a couple years, and he expressed it this way. He said, every morning you wake up for another day in paradise. Okay, it was just, he loved it there. I had a friend in high school, his older sister got married and moved out there, I think military again, her husband. She hated it because it was always the same. She got so bored with the temperature. Look, those kind of temperatures I could handle. All right, anyway, middle latitudes. That's where we live, okay? In between the tropics and the polar regions, the middle latitudes. Here you have higher solar radiation during one part of the year, that's when we're facing the sun, and lower on the other part when we're facing away from the sun. That's the tilt of the Earth's axis, okay? Overall, the temperatures are lower than they are at the low latitudes, but greater variation. We can be in the summertime hotter than the equatorial areas. Okay, that can easily happen. But in the wintertime, we're much colder than the equator, way colder. Okay, so our overall, the greater variation in different parts of the year, incredibly greater. Now at the high latitude, now you're getting up near the poles, either the North Pole or South Pole. Okay, the maximum amount of radiation is during one part of the year when that pole is actually facing toward the sun. It's still not a lot of radiation, but at least they get some. None on the other part, okay, when they're facing away from the sun. Absolutely no solar radiation ever hits the ground for days on end, sometimes months on end. Depends on how far north they are, okay? At these higher elevation, the overall temperatures are the lowest with the widest variation. Most of that variation coming on the low side, but they can go down. Whereas here in the middle latitudes, and we're in the southern part of the middle latitudes, our temperature variation would be from, a few degrees below freezing. Oh, wait, here comes Don. He must have had to get out and come back. I saw when his name disappeared here, but I already had him here. Okay. Does anyone remember what the low temperature was last winter? I cannot think of a day that got into the 20s. Can you? It had to have gotten into, yeah, that's what I was thinking. There may have been a few days in the upper 20s, but not very many. Now, that was not a very cold winter at all, okay? I would say we barely got our, supposedly the peach crop requires 200 hours below 40 degrees. I bet you they were awfully close to not getting that, okay? Um, it's, it was, I was a little scared that we might not have a peach crop this year, because we had such a warm winter. Now, we've had other winters that's gotten down. I can't ever remember, but maybe once or twice that we ever got below 0 Fahrenheit. Uh, I can very seldom remember in the single digit Fahrenheit, 8, 9, 10 degrees. I don't remember more than a handful of days where we've gotten that cold. When we get into the teens, we consider that incredibly cold. And it is. I mean, I believe lower 20s to me is incredibly cold. However, when I was in Nebraska, that's not that far north, but in Nebraska, that first fall term I was there, I had a final at night. This was in December. I was in the heaviest things I could wear coming back from that final exam. And as I was walking toward where I was living then, it was walking due south, I remember my face felt funny. I couldn't figure out what it was. What it was, my breath was freezing on my mustache, and I had ice all underneath my nose. Not frost, ice there. And all around my mouth, there was moisture had frozen on my beard. And that's what was feeling so heavy. And it was just brutal. And when I got home, I think it was the next morning, I heard the low that night was minus 17. I went, oh my goodness, no wonder it felt so bizarre, okay? And I determined then, when I was feeling ice, we were below 0, because I never felt ice here in the southeast. Up there, if I felt ice, I said, we're below 0 now. That was just my rule of thumb. Okay, and that's not that much further north, but, it was bitterly cold. Now, I also remember on Palm Sunday, which is fairly late in the spring, we had a snowstorm. I thought, this ain't right. This is not right. You do not have snow on Palm Sunday, okay? But they did. And I found out that year I was prepared for the intensity of the cold, but what I wasn't prepared for was duration of the cold. Because like I said, snow on Palm Sunday, by Palm Sunday, we're already in short sleeve shirts, okay? No, that wasn't right. I should not be wearing winter clothes on Palm Sunday, and yet I was, okay? No, that was in Nebraska. Yeah, that was when I was in grad school. No. Oh, wow. Wow. Yeah. So, high latitudes, though, when you're up near those polar regions, I was talking about below freezing Fahrenheit, they start measuring temperatures in the minus 70 degrees. No. That's why they say widest variation. If they get up to 40 and down to minus 70, that is a variation. Not that warm in the summertime, but compared to minus 70 in the wintertime, that's a huge variation. Now, this global warming stuff, I heard sometime this year, I think Roy said he heard it too, It's somewhere above the Arctic Circle. They topped 100 for the first time ever. Am I right, Roy? Did you say you heard that? I don't know. He may not be hearing me. Okay. So, climate and latitude. I can't get this thing to advance. Okay, this is the illustration of that. In the low lat, now this has the Earth sitting straight up. Picture it tilted, and you got a better view. But straight up, you see, even if we were straight up, 12 and 12, daylight, darkness every day, even if we were straight up, just like this, look at this. The incoming radiation comes directly into the low latitudes. I mean, goes through the least amount of atmosphere. Let's say the atmosphere extends out to here. That would be extending out to here, extending out to here. Okay? If I'm staying equal distance from the globe up here, and this equal distance here, look how much further it travels through the atmosphere, cooling as it goes. And then when it hits the surface, it's not hitting directly, it's pinging off. Here, it's hitting flat on. Okay, not quite flat, but pretty close. Here, somewhat tilted, here, way tilted. So that's what they mean by the angle of incidence of the radiation. Okay, the Arctic Circle is up here at 66.5 degrees north, Antarctic Circle 66.5 degrees south, Tropic of Cancer 23.5 degrees north, remember that one, 23.5 degrees south, Tropic of Capricorn. These are the low latitudes, these are the middle latitudes, and these are the high latitudes. Now, tilt the Earth and it even magnifies this. Now, if the sun's over here where it's coming from here, tilt the Earth that way, and you've got 24 hours of no sun here at all, and the North Pole is tilted this way. Down here at the South Pole, 24 hours of sunlight. However, it's not very warm sun, okay? That's when it may get up to 40 degrees or something like that, okay? Middle latitudes, where we are, extends our daylight and darkness by an hour or two. Go further north, like in Canada, and it extends it several hours. Go up here, and you may not ever have sunset, or never have sunrise. So those are reasons there, okay? Now, let's look at climate zones. Now, these are terminologies that again, this is over on page 589, the right-hand column there. Climate zones are defined in terms of yearly temperature averages, okay? And these pretty much follow what we were just talking about, the tropical climate zone near the equator, just like we were talking about before. It receives the most solar radiation, least amount of atmosphere it goes through directly, hits the surface, warms up. On the other extreme, the polar climate zone, the least amount of solar radiation, incredibly cold up there, constant daylight during the summer, part of the summer, constant darkness during part of the winter. Absolutely no solar radiation at all in parts of the winter. And we're in between the temperate climate zone. Temperate means in between the extremes. We're intermediate between the other two. We get more solar radiation than they do in the polar, but less than they do in the tropical, okay? We have some variation in daylight and darkness, but not as much as they do in the polar region. Now, this I think should be on the next slide. The rainfall pattern shifts seasonally. Hey, yeah, that's part of climate, but why is it mentioned when we're talking about climate zones here, suddenly you turn to rainfall patterns? But let's see. First, let's look at the picture here. Now, you see, it's not fixed straight lines. It's not exactly on the Tropic of Cancer and the Tropic of Capricorn. Here you have a temperate region below the Tropic of Cancer. Here you have a tropical region that goes above the Tropic of Cancer, okay? And similarly down here, You have regions that are temperate at the tropical below the tropic, okay, and temperate way above the tropic, okay. So you have waviness here, and that depends on other conditions, okay. Your look at down here in the southern hemisphere, your Antarctic Circle is down here, and yet the polar climate zone is way up here, okay. It's really cold for a long way. That's why this was the Cape Horn. It's the tip of South America. They said that was one of the worst places ever to try to sail in, ships to go around. That's what made the Panama Canal so important to commerce, because otherwise ships had to go around Cape Horn. That was awful, awful conditions there, because you were getting into polar areas. The winds were so strong, the temperature is brutal, okay. Whereas up here, there's part of the tropic of the Arctic Circle that's actually considered in the temperate region. All of Scandinavia is considered temperate, even though part of it is in the polar region, okay. Over here, parts of Siberia are polar, even though they're below the Arctic Circle. So you see, you have a lot of variation there, okay. Now, this is where the rainfall patterns come in, and this is, I think, a terrible view, okay. And I'll tell you why. This was realistic. Wavy, indistinct boundaries here. This is not realistic. All of a sudden you go here and jump up here and have a very wet. That's not how it happens. It may be very wet here, it may be dry here, but it's a gradual thing. It's not a sharp dip like this and that. This is just some artist rendition of it. This is not realistic, okay. But it's trying to emphasize the picture. Now, this is interesting here. Very wet, generally near the equator. Way dry above and below that wet region. And then wet above the dry region. So why is the discontinuity here? Well, that has to do with a lot of things: prevailing winds, temperatures, pressures, all sorts of things, okay. Poor old Mexico and much of South America turns out being mostly desert, okay. Whereas the U.S., look at us. Who would have thought we don't deserve it? We just happen to land right in optimum temperatures, optimum moisture. I mean, sure, we have some deserts in here, but they're nothing like some of these down here, okay. So, but this is highly idealized map. It's not very realistic. It does show the general pattern though. So let's look at regional climate influences. This is on page 590, which is 23-18. Okay. Regional climate influences. 4 major factors. One is altitude. Okay. At higher altitudes, the air radiates more energy back into space. Okay. I always thought it seemed backwards that mountain tops, I thought they'd be closer to the sun, so they should be warmer, but they always had snow on them. That didn't make any sense. But the reason is our atmosphere is like a big warm blanket, or layers of blankets, okay? And when you go up in atmosphere, you have less covering. You're on the blanket, you're not under the blanket. So up here at high altitudes, more of the energy goes radiating back into space, less of it stays inside the blanket, okay, because the blanket's thinner, okay? So altitude, that's one major factor in regional climate influences. Number 2, hey, wait, altitude mountains, aren't they the same thing? Well, it kind of is, but not quite. Remember the Tibetan Plateau? It's way up there. The level part of where the Himalayas are is still at a really high altitude. So they're really cold, okay, most of the time, even though they're probably closer to the equator than we are, but they're at such high elevation. But they're not mountains, they're on high plateau. Then they have the mountains, which are extremely colder. So again, the mountains are cooler at the higher altitude. So these do go hand in hand. Now, this is the best expression of the concept. Later you'll see a different expression of it, somewhere perhaps, but this is the best expression. The upwind slopes of a mountain, that means the air coming from wherever it's coming, hitting the upwind slopes of a mountain, that drops the moisture out. Because the mountains are colder, the air would have more moisture until it goes up the cooler mountains and then it rains. So the upwind slopes receive more precipitation, where the downwind slopes, now you're going from cold to hot. Well, you've lost all your moisture on this side, so you don't have a lot of moisture to drop on this side. So the downwind slopes receive less precipitation. Now, sure enough, that might be in our area, western and east, western slopes and eastern slope, but you go down to the tropical areas and the wind comes from the other direction, okay? So then it would be the eastern slopes and western slopes. So the best definition is upwind slopes, okay, and downwind slopes. That's why. When the air is going up a mountain, it's going to lose precipitation, so you get more rain there. And when it's coming down the mountain from cold to warm, it sucks up more precipitation, so you have less precipitation. All right, number 3, large bodies of water. Regional climate influences. To me, the most important thing in our climate is the Gulf of Mexico, because that's pumping moisture up into our area 12 months a year, okay? Maybe less sometimes than other times, but it is our supply of water, okay? High specific heat of water also moderates temperature changes, okay? Now what does that mean? You haven't had the chapter 4 when they talked about this, okay? Let me get something to drink. My throat is awfully dry. Okay. Have you ever been to the beach in the summertime? I'm sure most of you have, haven't you? Sometime or another? Like I said, my wife's family used to, about every 3 or 4 years, take a trip to the beach in the summer. And I can remember some of those trips. I really didn't care for the beach that much. I really didn't enjoy the trip that much. And I can remember, the further south you went, the hotter it got. It seemed like Montgomery was always 5 degrees or so hotter than Birmingham. You kept going south and it got hotter. And it just got hotter. And I thought, oh boy, this is so miserable. But then about the time you got to the beach, suddenly it felt cooler. Why? Because the soil has a very low specific heat. Solar radiation hitting the soil warms it up much faster than it warms up water because of the low specific heat of the soil. So sure enough, you get hot way faster. The water, though, has a very high specific heat. It takes more energy to warm up 1 gram of water 1 degree Celsius than it does to warm up 1 gram of soil 1 degree Celsius. A lot more, like 5 times as much heat, So therefore, the water will absorb more heat, absorb more heat, absorb more heat before it goes up in temperature as much. So therefore, the wind coming off the Gulf of Mexico, even though we're heading south, it always feels cooler because it's blowing across that cool water. Okay? That's in the afternoon especially. Okay. Early morning was when I liked the beach the most. I'd like to go out and take a walk on the beach. Shortly after, when the sun came up, it wasn't so miserably hot then. but then it was almost still. And the reason is your air temperature and your water temperature are about the same. So there wasn't that constant wind off the ocean. In fact, earlier in the morning, before I got up, the wind was actually blowing from the land to the sea. Why? Because the water maintained its heat, the soil lost its heat, so now it's cooler and the air flowed the other way. Okay, so large bodies of water moderate temperature changes. When I never really cared for going to the beach anyway, but when I liked it most, and I found out my wife liked it too, was in the fall and maybe early winter. You go down there, it's pleasant temperatures, not hot enough to lay out in the sun. That's what I didn't like doing, okay? But such pleasant temperatures. Why? Because the water in the wintertime holds more of the heat, the land loses more of the heat. So it was much more pleasant. Cooler in the summertime, warmer in the wintertime. That's my kind. Okay. And then the other major climate influence is that thing we don't understand, the ocean currents. They can bring water nearby that has a really different temperature from the land. We'll study this even more in the next chapter, chapter 24. But one of the big, again, as if we needed something else that was in our favor, in the U.S., we just happen to have the Gulf Stream. So even as far north as New York, Boston, things, inside, when you get inland, it's cold in the wintertime. Freezing cold. But the Gulf Stream brings warm water out of the Gulf of Mexico area down here, the Caribbean, and takes it up our seaboard, and those ports never freeze. Never freeze. Poor old Russia, sitting over there in the Pacific, the currents go the other way, and cold Arctic water is coming down, keeping their ports frozen several months a year. They were desperate to get a warm water port, and that's why all the hoopla about Crimea, the Black Sea is about their only reliable warm water port. Now they have to go through the Mediterranean and all sorts of stuff to get to the sea, but that's their only freeze-free port that they have. Everything on the west coast, on their east coast, freezes. So water currents, big regional climate influences. Of course, that's only if you're near the water. And here's what I was talking about. The water patterns are typically somewhat clockwise. So warm water comes in from the equatorial region into the Gulf of Mexico and the Caribbean here, and then it goes up our seaboard. Okay? And all of the eastern U.S. seaports are basically freeze-free every month of the year. Maybe up in Maine, they may get a little bit of icing there, but it's usually not bad. Poor old Canada, just to our north, there's a Labrador current that comes down here and freezes most of their ports solid in the wintertime. And they're just above us. Now, on the other hand, in the Pacific, again, just because of the way things are, there is a splitting current here. I've been in San Diego. I had some Navy school there when I was in the Navy, and may have gone to the beach a time or two when I was out there, but everything in San Diego, it's beautiful weather there, but it's never hot to speak of. Not ever the time I was there was it hot, but it's always so pleasant. But if you went to the beach, you usually didn't get in the water unless you had a wetsuit, even though it's way, way south, even in the summertime, because this California current is a cooling current, the one that comes like this, okay? Whereas over here, the Gulf Stream, in Long Island, in New Jersey. People go to the beach in swimming trunks in the summertime. They don't do it in the wintertime, but in the summertime. But in the dead of summer, you don't do it in San Diego. You have to have a wetsuit because it's just too cold. The water is too cold. However, we lucked out here again. This current splits here, and even though it should be frozen solid in the wintertime up here in Alaska, this warm North Pacific current goes like this, bringing warm water in, still cold like this, but compared to the soil, it's way cool, way warmer, and that keeps their ports ice-free. All along Alaska and even much of the, I think the Aleutian Islands, I don't think they ever freeze up, even though they're way north. Poor old Russia, though, the current goes against them. The same current that loops like this takes cold air, hot water from here and freezes all their ports. Too bad. Okay. So that's, if you're near the ocean currents can be big influencers of your regional climate. Whereas way south in San Diego, really cool to pleasant temperatures year round. Up in Martha's Vineyard, warm in the summertime, way too cold in the. Why? Because of currents. Now, how do we describe climates? Okay. This is over on our page. Whoops! Valerie, you let it slip. She usually alerts me. No, 4:15 we went through, but not 4:45. Okay, yeah, we're going to go through it, but I still need to call roll. So Valerie's still here, I think. Are you still here, Valerie? Okay. Don is still here. Harry is still here. Got to find you in the book. There you are. You're hiding from me, aren't you? Okay. Juan is still here. Okay. Nakaya is still here. Roy is still here. Okay, do I have everybody there? I hope so. Come on. Here we go. Let me scoot down. There's, oh, Scott. Scott moved up, so I almost missed him. Scott's still here. Okay, Roy's here. Oh, there's Scott come back down again. Okay, you're moving around on me, Scott. Thomas is still here. Keep on going down here. And Valerie, I think I already got you. Okay. I think they went back to alphabetical on me. Did I miss anybody? This is saying I've got 8 students here. I have 1, 2, 3, 4, 5, 6, 7, 8. Yep. Lost a few. While I'm here, Capri didn't make it in for the first half, or first part. Bridget didn't make it in. Patrick didn't make it in. Parisha didn't make it in. Kormisha didn't make it in. I take it because they make me take it. They say we need to do it for financial aid reasons, but that's only the first few weeks of the term. It may be that some things like VA or stuff, they may keep up with it, and some programs like workforce initiatives and things like this, they may keep up with it. And because some may, they make us take it for everybody. So I don't know. Jacob didn't make it in today. No, I don't. I grade you on how you perform on your test. Okay, that's it. Okay, now remember, there were a few things to be handed in, especially early in the term, but ever since then we've had tests and labs to be turned in, and those actually count. So So really the only things that you had to turn in early were your research paper topics and things like this, and that was only one deal. So not a big deal, but the thing is, usually if you're here, you do better on the tests and labs. Like if you're not here for a lab, it's hard to do well on the lab, okay? So, because we all talk about it. Let me finish here. David didn't make it in today, I don't think. Leon hasn't made it in today, so I think we're all right so far. All right, I just have to call roll because they make me to, okay? Okay, let me close this out then, and let's do describing climates. Okay, there's some problems, and this is what I was talking about in a couple of those earlier slides. There are no sharp boundaries, okay? What they sort of draw on a map as a boundary, it may be one side one year and the next year it's on the other side. I mean, there's no sharp boundaries. They're all gradual, okay? There's not suddenly it's this and suddenly it's that. You don't cross over a line and suddenly your climate changes. No, it's a very, very gradual change, okay? No two places have exactly the same climate. Now, there are some places that have similar climates. For some reason, north of San Francisco is very similar to the Mediterranean, okay? But they're not exactly the same, okay? They grow good grapes, they make good wine, you know, and that kind of stuff, but they're still not quite the same, okay? Even where I lived in Georgia is just about the same latitude as where I live now, but the climates aren't exactly the same. Similar, but not the same. They'll be a little drier over there almost always than we are here, and they'll also be typically a little hotter over there than we are here. That may have to do with the moisture too, I don't know. Okay? Now, a description of the North American climate zones follows, and to me, this is one of the better things in the book. Now, I just realized something I missed. I said that we were going to compare hurricanes and tornadoes. I thought they were going to show that, and they never did, and I missed it. Let me just refer you back to it. It just reminded me when I saw this table here. On page 586 or 23-14 is a listing of the tornado damage. Now, I'm not sure this is exactly the same scale they're using today. It seems like I heard they had revised this scale a little bit, but they're called EF tornadoes. And it can be an EF0, EF1, EF2, EF3, EF4, and EF5. I believe I'm right on that, okay? The fives were, we had like 3 or 4 of those fives that came through same time, different places in the state during that outbreak in April of 2011. I mean, that was just about the worst outbreak I have ever heard of on the planet for all time. I don't think any place had ever suffered that kind of widespread devastation for that long a period. I mean, some of those big heavy things stayed on the ground for miles and miles and miles and never seemed to lose strength. It just made no sense at all. They kept picking up strength every time they'd lose some, okay? So those are listed here, and you can look at the wind speeds. They give them both in kilometers per hour and miles per hour. Then on the opposite page, 587 or 23-15 are some of the similar type things for your hurricane categories. Now, they don't have a category 0 hurricane. They do have a category 0 tornado. So there's 6 categories of tornadoes, 5 categories of hurricane. Okay? And the interesting thing is the ones in hurricanes are a lot like the zeros in tornadoes. They just about all correspond that way, but there's nothing anywhere close to a EF5 tornado in the hurricane. Their most catastrophic only go up to about what the EF4 tornado does. So that's what I was going to point out to you. Everything is one step below, it seems like, what it is with tornadoes. But you have to realize hurricanes cover enormously more area than a tornado will. So it's more destruction. It's not as intense of destruction. I meant to point that. I thought the slide was going to show, and it never did. So anyway, here is the description of the North American climate zones. Okay? I say that and it won't advance. Here we go. So first, descriptions. Okay? We have marine climates. Those are the ones near oceans. Okay? This almost sounds like your air masses, and it's somewhat similar, okay, near the ocean. These are influenced by air masses from the ocean. So the marine air masses will be create or contribute to marine climates. Now remember, with marine air masses, you had tropical marine and you had polar marine. Quite opposite, okay, but that still is contributing to a marine climate. Then you have continental climate. Here you're far from the ocean, and your major influencing air masses are from large land areas. Like the northern plains are influenced mostly by continental air masses. Continental air masses coming south from Canada, polar air masses there are coming north from Mexico in the southwest, and they would be tropical continental influences. Okay, now in between those big groupings, you have lots of other classification. Arid means very, very dry, basically almost desert. Semi-arid is not quite a desert, but getting awfully close to it. Very, very dry, but not completely. Humid, that's what we have in the southeast, humid. And you'll see other descriptors like that as well. So let's move to the actual map. Now, this is hard to read from here. If you've got your book, it takes a full page on your book. Much easier to read there. So I'm going to read it from the book, even though I can read some of the things. Okay? The first one here, and this is North America. This is not, remember, this is back here. Description of North American climate zones follow. This is it. The white area up here, this is very northern Alaska, very northern Canada, and actually gets down the Hudson Bay here, goes pretty far south, and so this line is here. This is all considered polar up here. There's all of Greenland, there's all of Iceland over here. You know, this is all polar. And Roy, if you remember, we were talking about the magnetic North Pole. It's somewhere right in here in these islands north of the Hudson Bay here. Okay, so it may be over here somewhere by now. Yeah. Okay, I couldn't hear the last you said. Okay. I don't know. I don't have a globe in front of me to check, but I was thinking it was somewhere kind of in this region here. Is that where you were thinking? Okay, yeah, somewhere in here. North of Hudson Bay, somewhere in here. I may have had my cursor in the wrong place before. Okay, that's polar. Okay, after polar you have humid, continental, subarctic. Okay, that means plenty of moisture. Continental, though, that's almost a contradiction, but it's okay, it's correct. But subarctic, still very cold. Not as cold as polar, but still very cold. And that's why it can be continental and humid. There's not a lot of loss of moisture due to solar radiation. See, solar radiation tends to dry things out. You don't have that much there, so it stays fairly humid, but mostly because it's so cold, and largely because you have lots of water. Here's some lakes in here, Hudson Bay over here, the North Sea here. You know, there's just, no, I don't think it's called North Sea here. Bering Straits here. So you have plenty of moisture content, even though it's continental mostly. Okay. Then you have humid continental mid-latitude. That's the band that goes across here. And notice almost all the Great Lakes are in that band, plus some other lakes up here in Canada. Okay, there's the 5 Great Lakes. Erie's down here in the lower part, but the other, I think this is Ontario, Michigan. Is this Huron and that Superior? I can't remember. I at one time knew them, but I can't remember now. But that is your humid, even though it's not really near much water except over here, continental but mid-latitudes. And I'd say the humid comes from the fact that there's a lot of lakes in it. Okay, and it's still pretty cold, so it doesn't dry out as badly. Okay, next down is humid continental, and this called it low latitudes. Now that's not low latitudes like we were talking about near the equator. It's low latitudes for the North America, and that's this band here. And that basically is our farm belt right there. Humid, enough moisture to raise good crops. Low latitudes, and it's still continental, okay, but low latitudes meaning you have enough sunlight to grow good crops. Now, they don't maybe do too much farming here. They do some in New York and Pennsylvania and those areas, but boy, Iowa, I think Nebraska's in there, Indiana possibly is in there, Illinois, and then it goes up into Canada as well here too. And then this is where we live, humid subtropical. Okay, that's us right here. Now, again, I said one of the major reasons we are humid is the Gulf of Mexico. And frankly, I think this Gulf of Mexico pumps water into us, into here, maybe even up into here, because that is a huge supplier of moisture. Okay, humid subtropical, that's us. Tropical wet, okay, that's this bright blue here. This is called the Yucatan Peninsula. That's one of the few places in Mexico that you consider really, really wet. Okay, this is all, I mean, this is a tropical, it's definitely in the tropics. The Tropic of Cancer goes right across here, so it's definitely in the tropic, surrounded by water, and it shows it. It's very wet. Sorry. But then you have tropical with seasonally wet dry. This is the monsoonal areas. Remember, the tropical regions don't have that big a variation in temperature, but they do, for some reason, have large variations in moisture. So that's what you have here. And that's what Cuba is. That's what Hispaniola is. This is half or part of it. This part is Haiti, and that part's Dominican Republic, or I got them backwards. Here's Puerto Rico out here. That's part of us. And by the way, the very southern tip of Florida, that's Miami and probably the Keys in there, these are considered tropical with seasonal wet dry. Okay, this goes up the band here too. I think Costa Rica is right in here, and that's one of the more prosperous countries in Central America, and it has a pretty favorable conditions for weather conditions. Okay, and then semi-arid, and this is a mystery to me why this is semi-arid. Look at that. This is bordering the Pacific Ocean and is semi-arid. Now up in here, I know why that is. Mountains, okay, have blocked the moisture from coming in. Remember, the downwind side of mountains usually is drier, so that's why that is. Here we're bordering the good old Gulf of Mexico and still semi-arid. Poor old Mexico, they just can't catch a break. This is almost, not quite, but almost the border between Texas and Mexico here. This is slightly into Texas, and they're arid here. So semi-arid going up here, and again, the downwind slope of the mountains. The Rocky Mountains go right down through here. The downwind slopes are dry. That's here, here, and over here you have another mountain range. Okay, Sierra Nevadas here, the downwind slopes are dry. Okay, desert. And this is the biggest mystery to me. This is the Yucatan Peninsula I was talking about before. How in the world is it surrounded by water on the west, on the south, and on the east, the Bay of California here? Water, water everywhere, and yet it's a desert. Okay, that makes no sense. I don't know why it turns out that way. Here's my guess: those ocean currents. They must keep the prevailing moisture from coming in. I don't know why, but they must happen. Okay, and this goes down into the western coast of Mexico, desert, even though it borders the Pacific. Then right down the heart, the spine of Mexico. Now this is probably because of a mountain range here, desert. I'm not sure. Mexico City is somewhere right in here, so it's really, really dry. And then this is the deserts of our southwest. I want to say the Mojave Desert, I think, is in here, and some of the other deserts are here. Okay, the only parts of the U.S. that really don't get a lot of moisture. Okay, and then the marine. This is here. These are usually very wet areas, and this extends from just above San Francisco. There's the San Francisco Bay right there, I think, and it extends up here. The western slice of Northern California, Oregon, Washington, they just get rain, 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 because there's a mountain range here. They're on the upwind slopes of the water coming off, the air coming off the Pacific, drops all the moisture, because Mount Rainier is in here, all those mountains are here. The upwind slopes are wet, the downwind slopes are dry. And that extends up here. There's this, I think, is what they call Victoria Island off Canada. Vancouver is right in here, and then these other islands up here, and then you get into that little strip of Alaska that we have that comes down and rips off a lot of the coast of Canada. And all around here, it's considered marine, even though it should be very, very cold. Look at this. Way further south of here, that's considered semi-arid, and up here is marine, and they free of ice most of the year. Okay, and then this is that Mediterranean climate I was talking about. It's not exactly, and there's San Francisco and north of San Francisco. This is the oh boy, what do they call it? Goodness, the wine country there. What do they call that? There's some sort of valley. Napa Valley. Napa Valley is north of San Francisco here, very similar to the Mediterranean climate. South of it here, this is Imperial Valley, the San Joaquin Valley. All those really, really productive agricultural valleys are right in here. Okay, mostly fed by irrigation, grant you that, but the things that grow well in that, like grapes, they grow pretty well. Okay, and then you have the highlands, and these are the Sierra Nevadas here, and these are the Rocky Mountains here. Okay, and this is into the Presidential Range here and other areas like that. I think these are these are highlands down here too. And you see the upwind slopes get moisture, the downwind slopes do not. So these are highlands in here too. And down here, even in that narrow little peninsula there, you have some pretty tall mountains. And so that's a really good descriptor of these major climate zones. Now understand, the boundaries are not really fixed, okay? They will blur. Sometimes this will move this way, sometimes it'll move that way. You can't tell, oh, desert here, not desert there. No, it's not that distinct, okay? That to me is one of the more interesting maps. I love maps anyway. Okay. Their example 23.3 is a really good one, and 23.4. They give you temperature, precipitation, numbers and stuff, and ask you to figure out what climate zone you think they'd be in. And it's pretty reasonable to look at some of those. Okay. Let's move on. Now let's get to local climates. Okay. See how we're doing on time. Okay. Local climates can be fairly large areas or incredibly small areas, like a microclimate. It's a local pattern in climate in a very small area. Now, this can be associated with large cities, and I think we saw the blurb, I think last time, on heat islands and heat domes, and that's exactly what we've got. I think I described it driving from Bessemer to Birmingham in December. The temperature would start sort of chilly, maybe lower 40s, maybe drop a degree or two when I got out of Bessemer, going sort of north, sort of east, and getting later in the day. But then as I got closer to Birmingham, my thermometer started climbing. Not a lot, maybe 3, 4, 5 degrees, but it got warmer as I went up. Going north, going east, and later in the day, shouldn't have been going up. It was going up because of the heat island effect of a big city. Okay, and Birmingham isn't that big of a city, so bigger cities even more so. When I was talking with my older brother last night, the farm over in Georgia is way out in the country. Okay, way out in the country. And he was just talking about the temperatures, what temperatures they were seeing, because we're going over this weekend, and it's been pretty hot. But he said, of course, it's several degrees hotter in Augusta. I said, yep, the heat island effect. He said, yeah, he said, I call it the concrete and asphalt effect. Same idea. Okay, more covering of the soil by sources that absorb heat and release it. Then too, you've got more traffic, more cars, more buildings. The buildings, of course, even in the summertime, think about it. Air conditioning systems are pulling heat out of the air from inside, blowing them to outside. And these big buildings are doing that big time. So everything's contributing to more heat. And in the wintertime, more energy is being used to heat buildings, and some of that is escaping. So it's always producing more heat. The buildings and the pavement absorb and emit solar radiation differently from natural vegetation and landscapes. Just think about it. Now, we live in a neighborhood, and by the way, I may not have finished my story. When I drove into Birmingham, the temperature would rise. When I got off the interstate and started heading into our neighborhood, they start dropping again. Even though we live in Birmingham, we're in an area with lots and lots of trees and lots of parks and grasses and places where houses aren't living, or even where they are, they're underneath trees. So you can get a cooling, and I'd see that on my thermometer. It would drop off a degree or two. Not as much as it was outside Birmingham, but it would drop off from what it was driving through downtown Birmingham. Okay, the trees, just think about what they're doing. They're pulling energy from the sun and making chemical energy, converting the chemical energy, the carbohydrates, the complex carbohydrates, the cellulose, the sugars, whatever. They're pulling energy out and using it for different purposes, whereas buildings are not. They're absorbing it and later reflecting it. Now, this is sort of a stretch, but a local climate could be associated with a single tree. Lichens and moss grow on one side but not on the other. Now that could be because of sunlight versus no sunlight, north side versus south side. It could be because moisture on one side, not enough moisture on the other side. Okay, it could be a variety of things, and it could be differing in different areas. But they used to say in a given area, if you were good at it, you could tell where it was north by looking at what was growing on the tree. So that's where they stretch it down to, could be associated with a single tree. Now, just outside my window here, there's a lot more sunlight in the daytime. That's because last spring, I can't remember when it was, March, April time, may have been April, we had a gigantic oak tree, a white oak tree, that when I spread my arms and standing at the base of the tree, spread it, so about 5 to 6 feet up the tree, my arms around, I couldn't get halfway around the tree. That was how big that tree was. Towered up here. Now we're down in a low area, but it still towered up there. And last April, I think it was, one night we had rain, 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 day after day, week after week. And then one evening, no rain, no wind to speak of. I mean, just a little breeze or something like that. We heard something. The dog came racing into the house, scared half out of her mind. I went out to see. I thought an accident had occurred on the road because it's a bit windy road. I went out and looked. The tree had just laid down. I want to say fallen over, and maybe that would be a better word. Surely hadn't been blown over. There wasn't enough wind for that. It was late enough in the spring. It was fully leafed out. Not as big a leaves as they would be, but fully leafed. So it was healthy, but it just laid down. And one of the reasons, trees tend to go to the sun, so it was sure enough leaning to the south. A little bit to the east too, because there was competition to the west. There was no competition to the east, so it was just there. And it was a great air conditioner for us. In the wintertime, the leaves were off of it, the sunlight would come in. In the summertime, it was wonderful shade. It's gone. Okay, so our plants that are on that side of the house, they are having a very different year, because where they used to not get a lot of sun, they're getting a lot of sun. Where they used to be fighting for moisture from the ground, they don't have any competition anymore. So they're having, that single tree changed our microclimate definitely. All right, now they talk about climate change. Now, this book, I can tell the author is not a huge fan of climate change. But of course, he wrote this book several years ago. But he's still one of these, I think you come close to claiming him as a climate denier, but not quite. He does recognize there's climate change. Climate change is a departure from the expected pattern of climate for a region in time. Now there's the big key, for a region in time. Now, I think some of the conversations I've had with Harry on here about why the poles seem to be moving some, why, and we've had in class talking about the layers of the magnetic rock changing directions and that kind of stuff. Definitely over long periods of time you have changes. That's just part of nature. Everything varies over time. The axis rotation of the earth, okay, the tilt of the earth is slowly precessing. Over thousands of years is slowly changing, but it's making changes, okay? Now, sure enough, climate change follows a big, long, basically a sinusoidal curve. Warmer sometimes, colder other times, warmer other times. Admit, that's part of climate change, absolutely. Climate change is a departure from the expected average pattern of climate for a region of time. That last little phrase there, for a region of time. Now that's a weird way to express it because time doesn't have region, but you get what he's talking about. Okay? And here we're going to get to this in a minute. Now, they give us here, I need to check on something. Hold on just a minute. I'll be right back. Sorry, I should have paused the recorder for just a moment. My wife had to go into her office today. She has been working at home most of the time, but she's got some new projects starting, so she had to go in today. And she said, when I get back, you better close your door because I talked too loud. So I just had to close my door because I thought I heard her downstairs. So anyway, let's get back to this. Now, in recent times, we've been collecting relatively good weather data, but that's a sliver of time, very recent time. When we're talking about climate, sometimes you're talking about millennia of time, not years, not even decades, not sometimes even centuries, millennia of time. Thousands of years, okay? And if you talk about the Earth, millions of years up to billions of years. Now, we don't have anything going back that far. So the thing is, we've only been really measuring things for just a very brief part of time. I've seen or heard people talk about something. If you were to, on our back wall of our room here, you can't see it, but if you went from that wall to this corner over here, okay, that length of the room, I don't know, let's say it's 15 feet, maybe bigger, I don't know, okay, and you had all of the time the Earth has been here would be that wall, we would be just a narrow little pencil thickness over here in this corner. Okay, it's incredible. Okay, so we have very, very, very poor data for much of time, okay, that we're talking about. And that's why they say proxy data is used to infer past conditions. What do they mean by that? Okay, well, they drill down into ice cores like the Antarctic, Greenland, North Pole, somewhere like that, drill down into ice that's been accumulating over thousands of years and measure things as they go down. They can tell by different thickness and different amounts of carbon dioxide in the ice, different amounts of what life forms are trapped in the ice. All those things, they can just make guesses on what temperatures were like, on various things were like. And that's where this comes from. Now, this is still pretty recent. I mean, you're not even back at the birth of Christ yet, okay? This is starting, I'd say, around 900 AD. Now, that's a long time ago, but we didn't have weather stations. We didn't have things like this. I think Europe was still in the dark ages then. I mean, there was just nothing going on. Maybe in China and India, they may have had a little bit more going on, but I don't think it was widespread data. Okay? Now, if you think about 10 something another was when Norman French came in and invaded England. Okay? The 1200s, I can't think what happened then, but this was way, way back in history. Okay? Isaac Newton, seems like he was 1500, something like that. I may have that wrong. I've read so many papers on him, but I can't remember. I don't remember dates well. Now we get up in here, the 1600s. Things are beginning to change. The U.S. In 1492, Columbus scaled the ocean blue. So this is when the age of discovery started happening. They started keeping better weather data now, not just locally, but all over the place. So you started getting a little bit better weather data. And then the 1500s, 1600, the colonies were being formed in here. I think Georgia was a 13th colony, and it was around 1730 or something like that, 1750, somewhere like that. And then 20s or 30s. 1776, that's when we declared our independence. 1800s, we finally got our government running. France started, so we a little bit more civilization in here, okay, gradually happening. They started getting a little bit better weather information, and it's only been since the 1800s. Down in here would be the war between the states, that happens 1860 or something like that. And then late 1800s, early 1900s, you got into what we call the Industrial Revolution. Now, we started getting better data. We were collecting things better. We were getting much better equipment and stuff like this. But here is the part that scares me. Notice here, departure from expected average pattern for a region of time. Sure, this departure was above normal, this departure was below normal, this departure was below normal. That was normal for there to be these departures. But look at the time frame over which this change happened. To go from here to here only in maybe a decade, whereas to go from here to there took more than a century. This was about a decade, this was about a century. That's the big issue here. It's not that we haven't always had climate change, we have. But now things are happening so rapidly, we have to think, hey, are we part of this? Are we having something to do with it? Okay. Data about the ice ages, and there were more than one. There were like 4 really big major ice ages, and probably a few that were smaller. And interglacial warming, that means in between the ice ages when it warmed up. The ice ages were when it was getting colder, the interglacial was when it was warming. That show periods of warming and cooling occur in these really large cycles. Okay? Admit it. Yeah, that's true. Climate change has always been here. But during the past 100 years, the Earth has experienced 2 warming cycles. Okay? Now here was one, this is what they're saying, from around 1914 or so through 1941 or 42, there was a warming cycle. And then there was another one between 1965 or so till the present. Hey, again, these are more like this period right here. Okay? Yeah, when you spread them out, you see periods, but on the long haul, that's still a very, very rapid change from here to there in less than 100 years. That is a big change. Less than minus 0.4, let's say, up to positive 0.4. That's an 0.8 of a degree change. Let's go back, and that was in 100 years. Let's go back here. 0.8 of a degree would be about here, somewhere back here, to somewhere. It hasn't even gotten there yet. I mean, they didn't have that. They didn't get up to 0.4, but that took from before 900 to after 1200. That took well over 300 years, and it still didn't get as high as what we're talking about here. Okay, so you can't tell me what took 100 years here was well over, what did I say, 300 or 400 years then, and it wasn't even as big a change. Whoa, there's some differences happening. Okay, so sure, in the past 100 years, the Earth has experienced 2 warming cycles, but overall, that's 1 warming cycle. Okay, yeah, it got cooler in here for a little bit, but you can almost relate that to 1 or 2 major volcanic eruptions that put a lot of stuff into the atmosphere that blocked the sun's radiation. That was 1 or 2 catastrophic events could account for that. What accounts for everything else between here and there in such a short period of time? Now, the uniform changes are not uniform. The temperature changes are not uniform. Of course they're not. Volcanic eruptions are not uniform. Okay, there's lots of things not uniform, but look at the trend. The trend is still there. Now, they say here temperatures in the southeast United States have cooled since the early 70s. Well, that was before a few years ago. Okay, his data are old. Sea ice in Antarctic has increased. That was before a few years ago. Now they're losing sea ice like crazy down there. So you can't just take a couple of years and say that makes a trend. This makes a trend, or at least a part of a trend. That does. This little stuff in here, that's noise, white noise. Basically, this is the trend. This is a major trend. Okay? Wow, that is way steeper than anything seen before or since for a way longer range. Okay? So, I disagree with some of his generalizations. Okay? Now, the causes of global climate change. Yeah, this is the big argument. It's the result of complex interaction of factors. Admit it, sunspots have something to do with it, okay? For sure. That would be some of the white noise you see in there, okay? The Earth's tilt, orbital shape, and axis wobble. Yeah, but those are really long period of changes. Greenhouse gases, okay, we're getting down to it now. That's water vapor, carbon dioxide, methane, and other trace gases. The lab we're going to do next time, we'll be looking at some of these, okay? Those seem to have not huge effects, but definite effects. And sure enough, tropical deforestation ties in with some of this too, because when they cut down the trees in the tropics, number one, those are big carbon sinks. Those tropical forests pull in and store carbon out of the air, carbon dioxide out of the air, and put them into trees. Big trees, lots of trees. And then when they go in and cut them down to try to grow soybeans, boy, what do? Well, they can't harvest all those trees. They pile them in enormous piles and burn them. And when they burn them, they're giving off carbon dioxide like crazy. Okay? And then there's no more big trees to keep the soil in place and do all the good things those trees were doing for us before. Habitat for all kinds of animals and all kinds of bugs, everything was living there. We can't even imagine what kind of changes we're making. So yeah, these are definitely contributing. Sunspots, Earth's tilt, orbital shape, axis wobble, they've always been there. Okay, always been there. That's part of those big trends. These greenhouse gases, tropical deforestation, that's little term. That's recent. That's things that cause these sudden changes. And here's what he says about global warming. And parts of it kind of irritate me, but you've already determined that. Intergovernmental Panel on Climate Change, the IPCC, was established by the United Nations in 1988. Again, we're talking about a pencil width, period of time. Okay? Now, here are some of the typical weasel words that are used. Despite research, data, and models, the predictions of experts vary. Wait a minute. Wait a minute. You talk with experts about the coronavirus. Yes, predictions are going to vary. Some will say a year or two, some will say 3 or 4 years, okay? If it's something someone knows almost nothing about, especially if they're building models with limited data and very little research behind them, yeah, predictions of experts are going to vary big time. But what he's not saying here is 95% of the professionals all say it's happening. Yeah, their predictions may vary in degree, but they all say it's happening. There's maybe 5% there that are climate deniers, okay? I don't know what's wrong with them. The data are there, but they still refuse to believe it. When 95% of the experts are basically agreeing on the big picture, I say let's go with them, okay? He tends to say, oh yeah, but these are varying. Of course they vary. Now, this statement here really bugs me. Critical analysis of climate change should be completed before future policies about human-made carbon dioxide are implemented. You know what bugs me about that? When will we ever completely form critical analysis? As soon as we learn something, we learn some other question, we start investigating that, then we'll do that. When are you going to complete those? Let me tell you when it's too late to do anything about it. So to say that they should be completely finished before any future policy are implemented, that's nuts. That is totally nuts. When all the indicators are here, all the indicators are pointing this way to say, no, but we don't know all the answers yet, so let's not do anything until we have all the answers. By the time we have enough answers, it's going to be too late. Now, this is a dumb analogy to this, but it is one. I don't think my older brother was really taking the coronavirus all that serious. He lives way out there in the country in rural Georgia. They had very few cases. There was only one spike of cases that made their county even on the map, and that's because there had been a funeral, and at the funeral, evidently there was one person who was infected and without symptoms, and at the funeral there was probably a lot of hugging and stuff like this, and after that funeral they had a bunch of deaths, including the pastor who presided over the funeral, and a bunch of cases. But they kind of, but that was just that one church and that one freaky set of events. So they weren't taking anything seriously. I talked with him on the phone last night. He said, Mike Harrington died of COVID. Mike Harrington was a classmate of his. Suddenly, a death reached close enough to home. He said, yeah, things are getting pretty bad here. Before that, hey, it's not hitting us. After that, things are pretty bad here. Well, if we wait until we've completed everything here, it may be things are pretty bad here, and it's going to be too late to do anything about it. So, I don't know. Sorry, that's my soapbox. I should get off of it and let the author do his business. He's much smarter than I am. But anyway, that's what I got. Now, on page 596, there's a good picture of what he's talking about, sunspots. For some reason, there are various things that are happening on the sun that produce these spots. That's where the temperature suddenly gets a lot cooler, I think. Other times, they're not happening. Well, when these are happening, a lot of radiation is leaving the sun and hitting the earth, making our climate and everything different. Absolutely, without a doubt, that contributes to climate change. The big, broad picture of climate change that we've always had. Yeah, but they've always been there. Nothing really has changed about sunspots that I know of anyway. Okay, what has changed is how much carbon dioxide, methane, and other things we are putting into the air. There was a book published, and I know it was somewhat political, so I know some people may not agree with it. It was called, goodness, I can't think of the name of it, An Inconvenient Truth, okay? And it had in there a map that was a lot like this one, showing that increase there, and happened to show right next to it the carbon dioxide content of the air, and the slopes were almost identical over the same ranges, and that basically represented the Industrial Revolution. Hey, same time period, same slopes, same. Hey, how can you argue with that? Okay. Now, the next page, a case study here. This is a great read, by the way. Please read this one. Okay, El Nino. And remember when the little statement was made in the book, we need to know a lot more about what's happening in the oceans? El Nino is an ocean event, and as far as I know, nobody knows why it's happening, but they know when it does happen, it changes our climate, it changes our weather big time. Not climate so much as weather. So that is a definite read. Please read that. Really interesting. El Nino is one, La Nina is the other. One goes one way, one goes the other. Okay? There's another pretty good little blurb here, and this is this one on, and I can't begin to pronounce his name. Okay? I'll give it my best shot. Wilhelm Firmin Kolleren Brzezinski, or something like that. Okay? Norwegian, if I've ever seen a Norwegian name. They say basically created modern meteorology. Okay, so well worth a read. As you read it, you'll see possibly some other things that would give you reason to want to write about something related to it. And then this is the one that shows the carbon dioxide emissions. Look at those dates, 1870 to 2010, and go back to basically this part here is kinda like this sort of flatter part in your book. Not quite flat, but a little. It's a gradual increase. And then when the steep increase comes, that's the part right here. I mean, they correlate so incredibly scarily. Okay, it's just pretty amazing. So there's another really good blurb. And I think that is this one on that we just hit, global warming, was the last slide in the chapter. Now, how are we doing? We got about 30 minutes left. I say this at the end of a chapter, especially this chapter. I mean, every chapter is this way. Please read the chapter. Please read the things about El Nino and things like this. Well worth your reading. Hopefully it'll make what I've said more sense. You might find things you think are contradictory. Fine, read it. Okay. The summary here summarizes then, after you've read the chapter, it's about average, maybe a little below average in length. The key terms, again, around average, possibly a little below average. Key terms are given alphabetically, however, they do give the page number where they're first either defined or described. But the very best thing for studying for this test would be applying the concepts. And this has 45, which may be just a little bit below normal questions, but the answers are given. If you know these, you have a really good shot at doing quite well on the test. Question for thought, 14, maybe a few below average, but pretty close. Further analysis, right around average, maybe a little less. invitation to inquiry, that might be something you might want to look into as a potential paper topic, but I don't see it, but you might. Parallel exercises, especially, well, again, a lot of these are based on assumptions that you had the first half of the book, which most of you haven't had. If anything, questions 11 in both group A and B would be going back to that table I said was such a good one, to find the principal climate zone. Actually, two of those, 11 and 12. However, there's no answers in the back, so I don't think on either group, so can't do much with that. All right, any questions on chapter 23? And for those who may have come in later, after I said it, let me go over this again. Today we're going to start in 24 in just a few minutes and only get barely started on that. On Monday, we will continue in chapter 24 and hopefully get a pretty good chunk of it done. But at 4:15 we'll stop and have the lab from chapter 23. And like I was saying, I've got most of the lab worked out on paper, but I have to type it in, and I have very little time to do so, so I've got to get that done. I don't know when, but I've got to get it done. I'll try to have that ready Monday by class. So the last 2 hours Monday will be that lab. It's going to be mostly on global warming. Let's see, actually, did I have a title here? No, greenhouse effect, which has to do with global warming. Okay, so that's going to be the lab for Monday. Then on Wednesday of next week, we will hopefully finish chapter 24 and have time to do its lab. Its lab is really short. It's based on the book, not on anything else I'll go to. This lab here is based on one of those laboratory simulations like we did with plate tectonics. Okay, only this one's, I think, a little bit better to do, and I think it'll be easier to do too. Okay, so that's going to be, and so Wednesday hopefully we'll finish 24 and have the lab on 24, which is based almost completely out of the book. You probably can get some of the answer, most of the answers online somewhere, but you're going to have to do some digging. Everything on that lab I got out of the book. So if you got your book, be prepared to have that with you on Wednesday. And then at the end of class on Wednesday, then I will give you both the chapter 24 test, which is a pretty straightforward test, and the final exam. Okay, and the final exam, like I was telling people earlier, I don't think it'll take you 30 minutes to finish. It's really simple. Matching covers the big topics in all the chapters we covered. 2 or 3 of the big topics, you match them up, it should be pretty easy. Chapter 24 test is going to be, I think okay too, about like all the others. Okay, so that's how we're going to wind up. Now, as I told people early at the beginning of class, please, if you can, get me all of your research papers, your labs, and your tests that you have in your possession now or that I've assigned before. I have, I'm guessing, less than half of your work in. Okay, most of the ones who are here, I have most of your stuff. It's the people who are not here, unfortunately, that I'm missing most of it. I don't know what's going to happen then. May have a lot of incompletes, I don't know, but please get your stuff in. Okay, if you can, get it into me today, tomorrow, it's Thursday. Friday morning, I'm going to be out of town. We're leaving town early in the morning, and where we're going is the farm in Georgia. Almost no, really slow and poor internet service there. So I'm not sure I'll be able to get anything. We don't even have a printer over there because our internet is so bad. So it'll be Monday when I get back that I'll be able to pull some of that off, and I'm not going to have a lot of time to do that. So please, if you can, get me as much as you can today and tomorrow. If you've already got some tests and labs finished and you just haven't sent them to me, please send them to me, okay? If you are close to finishing, try to go on and finish them and get them to me today or tomorrow. Otherwise, get them to me over the weekend, so when I do get back from the weekend, I can print them off and try to start grading them. Don't hold off. Yes? Okay. Okay. That one research paper, remember, it's in the syllabus. We went over this the first of the term. It counts as a full test grade that cannot be dropped. You can drop your lowest test grade on the chapter tests. You can't drop the research paper. You can't drop the final exam. So please get me something. Even if it's not your very best work, get me something. A 0 is really hard to pull up. Though we've had what I think we'll have 7, 8, or 9 tests, so you'll be able to pull it up some. But if you get me something, it won't be a 0. Okay, it may not be a great score, but at least it won't be a 0. So get me something, please. It's not droppable. That was in the syllabus. I tried to emphasize that at the first of the term. Okay. Now the labs are going to help you. If you got them in, they'll help you. If you don't have them in, they're going to hurt you because they're 25% of your score. And if you've gotten, I will drop either 1 or 2 of your lowest lab scores, depending on how many come in, how many we wind up doing. I will drop your lowest test score, not counting the research paper and not counting the final exam. But I will. So you will have some ways to improve things, but they can also bite you. So I know you've turned in most of your labs and they've been quite good, so that's going to be a big plus, but still only 25%. A 0 on that research paper hurts that 75% big time. So please get me something. Okay. Yeah, of course. That was for somebody else in case that. Yeah, okay, got it. All right. So let me get out of the slide set for chapter 23 and get into the screen share for 24. Okay, I think this is the one that blows it up. Okay, and we'll go to, okay, can you see my slide right now? The Earth's waters? Okay, it says on my screen, screen sharing is stopped as the squared window is closed, but it's open again. Okay, so you can see this, chapter 24, Earth's waters. All right, good. Beautiful picture of the ocean here. Very similar to the one in the book, only the one in the book, it's a yellow sky and a reddish ocean. This is a reddish sky and a bluish ocean. So slightly different time of day. I think the other was in the morning after sunrise. This is just before the sun setting, whatever. Here is the core concept for this chapter. If I can get it. Oh, wait, I've got to get some things out of the way here. By the way, my internet bars are pretty low here, but we haven't had any problems, knock on wood, so far. Okay, so let's see if this will, no, it still won't advance. All right, here we go. Here's the core concept. This is on page 606 in the book, which is 24-1 in the small book. Earth's waters. The hydrologic cycle. Now, how many chapters have either started or ended with a cycle? The rock cycle, the this cycle, that cycle, the uniformity, whatever. Everything. The global warming cycle, okay? Everything follows in cycles. The hydrologic cycle is the evaporation of water from the oceans, transport by moving air mass, precipitation across the surface, and movement back into the ocean. There's the cycle over and over again. Okay? Now, there is a great illustration, I wish I could find it, showing percentages of the water on the earth. And they have, I think, a big barrel that would represent the oceans. Then they have a pretty good sized pot over here that would represent the glaciers. And then they have a glass of water about like this that would represent surface fresh water that we have access to. It is amazing, the relationship there. If anyone can find something like that, that'd be worth maybe writing a paper on. Okay. Now, first topic here, 24-1, water on the earth. Okay. Water is by far the most abundant chemical compound anywhere close to the Earth's surface. Okay? It covers a full 70% of the whole Earth's surface. Okay? 97% of that water is in the oceans. The oceans are enormous. Only 3% of that water that covers the surface of the earth is fresh water. 3%. 3% fresh water, stuff you could drink. Only 2/3 of that fresh water is in ice caps, or at least it used to be when this book was written. The trouble is these are shrinking daily, okay, or almost daily, okay? So that means basically 2/3 of that fresh water is in ice caps. I mean, 2/3 of the total water is in, and that's of the 3% that's fresh water is in ice cap. 1/3, which is 1%, is available for us to drink, to use, to water plants, to flush toilets, to do bathe, whatever we're going to do. Okay, raise crops, whatever. It's still a lot of water though. Okay, that's the thing. The hydrologic cycle, as mentioned before, covers first the, well, wait. Let me back up. Here is an illustration of all the water. The most prevalent chemical on the planet, on the surface of the planet, is all of these, and they actually say almost 98%, 97.6% is ocean water or salty water. Fresh water is just a tiny little sliver. I wouldn't like someone that gave me that piece of pie. Okay. Now, of that fresh water, let's blow that up into this whole into this whole circle here. And up here it says 2/3 with an ice cap. This says almost 80% of it is locked up in ice. I think this was done before this was done, and this is probably out of date now. Okay? Now, so more than 2/3, something like 80% locked up in ice or something in there. And then underground, and we call these aquifers and things like this, that's most of that 20%. Okay? In fact, almost 21%. Your rivers, lakes, and streams, that piece of fresh water is minuscule. Minuscule. And even smaller than that is the small amount of water vapor that's in our atmosphere. That's 0.004%. Okay? Which if you wrote as a decimal number would be 0.00004. Okay? An incredibly small amount is in water vapor. Okay? A very small percent is in rivers, lakes, streams, what we consider fresh water. Most of our fresh water is underground that we can use. Some of it we haven't gotten to yet, thank goodness. But then huge amounts of fresh water is locked up in ice. So we do have plenty of water, but the distribution of the water is not particularly good. Okay. Now, here's the hydrologic cycle. I think you may have seen this in the earlier chapter 2. Water, like 70% of the surface of the earth is covered with oceans. And especially near the equator, lots of that is covered by ocean. And all that receiving heat from the sun evaporates the water out of the ocean. Now this that's evaporated is pure water. Pure water. No really contaminants in it. Every now and then a few salt crystals or things like this go up, but very, very little. Okay? This moves up until it reaches high in the atmosphere where it cools off a little and settles out as clouds. The prevailing winds blow the clouds over. Now some of the clouds rain back in the ocean. That's a short circuit. But that's a hydrologic cycle there. It's just a short circuit. Okay? The beneficial clouds make their way all the way to land, and then when they hit a mountain range or just the cooler temperatures here, they precipitate, drop the water out, and that falls onto the earth. Now, if you look at these percentages, they're rather bizarre. The evaporation from the ocean is 84% of that water going into the atmosphere. They don't mention anywhere, oh yeah, here they do. The other 16% is coming off the land, off the lakes, off the rivers, and just evaporating off the land. So most of that goes into the atmosphere is from the ocean. Well, the ocean is just solid water, the land is not. Whereas the oceans only cover 70% of the surface of the world, 84% of the moisture that enters the atmosphere comes from the ocean. Only like 16% comes from land. So that's these two percentages tie together. Now, of that water that falls from the clouds back to the earth, 70% fall right back into the ocean. That's a big short circuit there. Only 23% of this actually falls onto land. And 23% and 77, that adds up to 102. So 3/4 of it goes back into land, less than a quarter goes back. Back into the ocean, less than a quarter falls on land. But of that does fall on the land, 7% of that goes right back into the ocean. Hits the rivers, hit the mountain, whatever it does, goes downstream and makes its way back in. That means only 93% of that little bit of precipitation that does hit the land, well, 16% goes back into the air, 7% goes back into the water, but these are different percentages now, okay? Now, the rest of this, fortunately, makes its way into the soil, either to be used by plants, then to be re-evaporated again, or whatever other purpose it has, or to go into what we call groundwater. And we'll talk about all those things later. Okay? Now, let's look at the first subtopic here, and this is your fresh water. That's that tiny little sliver, but we're going to talk about that first. Where does it come from? Precipitation. Like we said before, evaporation from the ocean is pure water. Okay? Pure water. Makes its way into the cloud. Now, there's some dust, stuff like that up there, and a few salt crystals and things, but most of it is really good fresh water. Makes its way onto land, and that's what precipitates and falls. Fresh water. Now, precipitation is the basic freshwater source. Now, like we said, okay, and this is something else. 2/3 of that fresh water that falls onto the land goes right back up into the atmosphere. It evaporates again. The remaining 1/3 splits up a few ways. Either it runs off flowing downhill, or it's absorbed into the soil. Oh, that's good stuff. Now, even that is absorbed into the surface may wind up reaching and emerging somewhere else as runoff. We'll see pictures of that later. Now, the runoff and also groundwater distribution depends on several things. One of those things is the soil type, also the soil dryness, also the amount and type of vegetation, and certainly the steepness of the slope and the rate at which it rains. So all these things determine how much runs off, how much goes into the groundwater. So let's look at soil type first. If it's falling on a sandy soil, it's getting sucked into the ground, okay? Because sands have big particle size, big soil pore spaces, lots of opportunity for the water to go in. Now, even if it's gravelly soil, that's even better as far as absorbing the water, okay? A clay soil, those particles are really tiny, so their pores are really tiny, so it takes a long time for water to make its way down. So the clay soils, not as good, okay, for getting it. More will run off, less will make it into the groundwater. Now, this is bizarre, the dryness of the soil. And this is a strange thing, but when a soil is super dry, it gets to be what we call hydrophobic. It's actually scared of water, you might say. If the water hits it, it beads up and tends to run off. Because the soil has gotten so dry, it's lost its potential to absorb water. So a very dry soil cannot take a heavy rain. It runs off, it erodes pretty badly. If a soil is slightly damp, then there's lots of pathways for that water to get into it. We used to, when I was growing up, we raised chickens, not for commercially, just for our own use. We ate the eggs, ate the chickens, the roosters anyway, and occasionally an old hen, but not most of the time, not. But anyway, in the hot part of summertime, anytime we were processing stuff from the garden, we had a big garden too, and we'd go to throw it out, we'd throw it into the chickens so they could pick at it. And I remember noticing when it was really hot and dry and the chickens would just pick all the vegetation off, the soil would just be lying there, throw that water with the other stuff in it, the water would beat up, almost like on a wax car. It would beat up and be hard for it to absorb into the soil because it was so dry. If a soil is slightly moist, it actually absorbs better. Now, if a soil is already saturated with water, like a lot of our soils have been this spring and some early summer, it's hard for them to take any more. So that will also contribute. So there's all sorts of ways these relate and interact. Now, the amount and type of vegetation. If you have nice, thick turf, grass, that is wonderful for absorbing water. Because grass roots are small, tiny, they make little openings, lots of opportunity there. Trees, sometimes near the base of a tree, they shade so badly you don't get great vegetation, and trees will sometimes run off worse than grasses will. But it's still better to have trees than not having trees. Okay? Now, not only vegetation, but residue from vegetation. If any of you are gardeners, if any of you are landscapers, like to keep your yards nice, you know in those flower beds, in those vegetable beds, if you can put down a mulch, you're going to absorb more moisture and keep more moisture. Why? Because less moisture is returned to the atmosphere. 2/3 go back to the atmosphere. If you have a nice coating of grass or other plants or mulch, then it sucks in and doesn't as much evaporate away. Now, of course, steepness of slope. That's why I said before, we have a hillside here. It's really steep. Nothing much we can do to keep the water. What I did when I tore up I had them tear up a concrete, I don't know what you call it, just a concrete surface in the back of our yard, had them break it into, I said, try to get in 1 foot square pieces. I built terraces with that, and then when we dug out our patio, I filled in behind the terraces so it would slow the steepness. The terrace was the steepness, well, you're not going to erode there. Slow it down, and then where we have to have our path down, I try to keep a mulch on it to keep the water from flowing downhill. So the steepness of slope, there's not much you can do except terracing and trying to keep it mulched. The rate of rainfall. I love those nice slow rains because most of that's going to soak in. Those heavy downpours, much of that's going to run right downhill. It doesn't have time for it to run it. So the rate of rainfall. So all these things interact like crazy. Okay? Here's sort of an illustration of that. If you have steep slopes, then you're going to have more runoff. If you have a gradual slope, maybe that'll hang around a little bit more. Okay? This does make its way into the soil on the gradual slopes, goes into the groundwater, but at some point down here, the groundwater goes into the stream and may flow downhill as well. So this is illustrating several of those. The groundwater absorbed into the surface can emerge elsewhere as runoff, like groundwater going in here can join the stream down here and ultimately run off as well. Okay, now put lots of grass or trees here, you're going to slow down the runoff. Okay, and you also keep erosion from happening, making your stream bed cleaner. So lots of advantage for having plant life or mulch of some nature on the soil. Okay, all right, 2 minutes. Do we have time to do this slide in 2 minutes? Let's see where we are. Probably not. Not the way I talk anyway. So this is where we'll start next time. Okay, do you mind if I cheat you out of 2 minutes of your tuition dollars? Sorry about that. Any thoughts, last shots, parting shots, any questions, issues, especially on getting work turned in as soon as you can? Okay, anything there? Okay, anybody else? Okay, please folks, like I said, try to get me your research papers in. Get me something, okay? Try to get your, especially those old labs and tests that you've been hanging on to for, or maybe never even printed. Get those done, folks, please. Try to get them done today or tomorrow if possible, okay? The stuff, I'm going to try to give you your test on chapter 23 later this evening. I don't know exactly what time, but I'll try to get it done this evening out there on Blackboard message, okay? And then Monday, before Monday, I hope to have the lab done up. I haven't put, oh yeah, the lab simulation's already under content, and I'll explain to you in the lab how to access that. So that's already there, but you just don't know how to access it. Okay, that'll be in the lab. And then try to get Monday's lab done by Wednesday if you can, and we'll be doing it in class all together. So please be here Monday. Okay, don't say, oh, I'm tired of listening to them talk. Hey, get the lab done on Monday so you can turn it in Monday or Tuesday or early Wednesday. Okay, and then I'm a little distracted because there's an awful lot of smoke coming out from near one of the houses behind us here, and I hope someone's grilling out, but boy, that's a lot of smoke. Okay, never mind. Okay, and then Monday we'll have the lab for chapter 23, hopefully make a lot of progress on chapter 24, and then on Wednesday hopefully finish 24, do the lab for 24, and I'll give you the final exam as well as the test for 24. So that's a lot right at the end, but if you're with me in class, we can go through most of the lab together unless you just rather do it on your own. It's going to be pretty simple, and then the test will be pretty straightforward for 24, and the final exam will be very easy. So please be ready for that. So any last thoughts, parting shots? I'm going to stop the sharing here. And unless there's some comment, I'll end the session. Take care. Okay. You do too. Thank you so much.